The continents of Earth have drifted slowly across the planet's surface. Today, familiar shapes like Africa, Asia, and the Americas seem permanent and strong. And many people imagine that the story of global geography truly begins with Pangea, the giant landmass that existed many millions of years ago. But Pangea was not the beginning. It was only the latest chapter in a much older saga. Scientists have evidence showing that other supercontinents rose and fell long before Pangea ever formed. These were ancient worlds with no dinosaurs, no forests, and in some cases, no complex life at all. A primordial continent, or even a chain of supercontinents, may have formed, collided, shattered, and sunk back into the deep mantle, leaving almost no trace on the modern surface. An entire continent could vanish, its mountains ground to dust, its crust recycled into the interior of the planet. This lost world is one of the most dramatic geological mysteries on Earth. Geologists study scattered fragments of ancient crust, called cratons, tiny crystals known as zircons, and faint magnetic signatures locked inside the oldest rocks. Together, these clues suggest that supercontinents like Valbara, and Kenorland existed billions of years before Pangea, yet the coastlines, mountain chains, and full shapes of these vanished lands have disappeared. What did these continents look like, and how did they die? To answer that question, it is necessary to travel back into an environment far more dangerous than the age of dinosaurs. Early Earth was a violent world. Vast regions of the planet glowed with magma oceans. Asteroid and comet bombardments repeatedly struck the surface, releasing enormous energy and reshaping the crust. Later, global ice ages may have locked the planet in frozen conditions from pole to equator, as thick ice sheets scraped and cracked the young continents. In such an extreme environment, even the strongest rocks could be torn apart and driven downward into the mantle. Scientists have built a picture of this hidden history by combining many lines of evidence. Some zircons from places like the Jack Hills in Australia are over 4 billion years old, older than any known mountain range, hinting at even earlier protocontinents that no longer exist. Paleomagnetic data from South Africa and Western Australia suggests that pieces of crust once sat side by side, forming Valbara, perhaps Earth's first supercontinent. Later, landmasses such as Kenorland, Columbia, or Nuna, Rodinia, and Gondwana played an important role in shaping oceans, climate, and the conditions that would much later allow life, including dinosaurs, to spread across the globe. In this episode, the story will follow those traces. Ancient cratons buried beneath modern shields, microscopic zircons older than any fossils, and magnetic signals frozen in stone. Step by step, the reconstruction will move from the earliest supercontinents to Pangea itself. Somewhere, hidden beneath modern oceans and locked inside the oldest surviving rocks, lie the last fragments of a continent that predates Pangea by billions of years. Can the scattered clues of bones, crystals, and magnetic fields finally reveal a world that vanished without a trace? To understand that vanished world, the map of Earth itself must be rewritten. Imagine almost all of the planet's land welded together into one gigantic, continuous block of crust, ringed by a single, endless ocean. That is a supercontinent, not just a large continent, but a world where coastlines shrink, interiors stretch for thousands of kilometers, and the global environment is reshaped by one massive landmass. Such giants do not appear only once. Scientists have evidence showing that Earth follows a repeating pattern known as the supercontinent cycle. Over hundreds of millions of years, scattered continents drift together, collide, and lock into a single powerful cluster. Then, slowly, heat trapped beneath this thickened crust tears it apart. New oceans open, old oceans close, and the cycle begins again. It is one of the most far-reaching rhythms in the planet's history. At the heart of this cycle is plate tectonics. Deep inside Earth, hot rock in the mantle rises, cools, and sinks in slow convection currents. These currents drag the rigid plates of crust above them, forcing some to collide and dive back down in subduction zones, while others stretch and split along rifts. The result is one of the most dynamic and dangerous planetary surfaces in the solar system, with mountain building, earthquakes, and volcanic eruptions all linked to the same hidden engine. Over time, this engine has assembled several supercontinents long before Pangea. The earliest widely discussed example is Valbara, which may have formed more than 3 billion years ago, when Earth's surface was still young and hostile. After that came Ur, then Kenorland, each marking a stage when ancient continental fragments, or cratons, clustered together. Later, a vast landmass called Columbia, also known as Nuna, drew many of these cratons into a single framework. Rodinia followed, reshaping global oceans again, and finally Gondwana formed in the southern hemisphere, a strong continental core that later played an important role in building Pangea. Pangea itself formed many millions of years ago in the late Paleozoic, long before dinosaurs evolved, but close enough in time that its outline is still relatively clear. It is famous because its breakup created the continents that exist today and set the stage for dinosaur ecosystems on separate landmasses. Yet in the long sequence of supercontinents, Pangea is recent, well-preserved, and in many ways the least mysterious. If Pangea is like the last big battle in a long war, then Valbara, Ur, Kenorland, Columbia, Rodinia, and Gondwana are the earlier campaigns that quietly decided the outcome. Their assembly and breakup controlled sea levels, climate, and the chemistry of oceans and atmosphere, shaping the environments in which early life struggled and later flourished. Scientists have only scattered rocks, tiny crystals, and faint magnetic signals as evidence, but these fragments point toward continents older than complex fossils, older even than the air that later dinosaurs breathed. To trace them, geologists must search in rocks so ancient that the original land they belonged to has completely vanished. Where did those first continents go, and what hidden worlds did they once support? To answer that, the story must move far beyond the age of dinosaurs, back to a time when continents themselves were fighting to exist. More than 4 billion years ago, Earth's surface was not a mosaic of stable lands and calm oceans. It was a blazing world of magma seas, erupting fissures, and a choking sky heavy with steam, methane, and volcanic gases. During this early period, the planet's outer shell was so thin and hot that it behaved almost like a liquid skin. Vast regions of molten rock stretched for thousands of kilometers, hardening only briefly before new waves of lava buried them again. Any early crust that tried to rise from this ocean of fire faced a hostile environment where solid ground was temporary and fragile. Above this unstable surface, the atmosphere was thick, toxic, and dark. There were no plants to release oxygen, no soils to soften the landscape, only bare rock and boiling water. Lightning storms raged through dense clouds, and volcanic plumes rose higher than modern jet aircraft. In this environment, even a short pause in the violence was rare. The planet was built to erase its own past. Then came one of the most destructive chapters of all, the late heavy bombardment. For many millions of years, asteroids and comets slammed into Earth with incredible energy. Some impacts were powerful enough to vaporize oceans, melt entire regions of crust, and throw glowing debris halfway to space. Craters overlapped craters, and each new collision reset part of the geological record. Scientists have evidence showing that this bombardment repeatedly stripped away or buried the earliest surfaces. Any small protocontinent that managed to form was attacked from above by falling rock, and from below by intense mantle heat. Under these conditions, survival of ancient rocks was extremely rare. Most early crust was either melted, shattered, or pushed down into deeper layers of the planet. This is where another destructive force played an important role. Earth became a self-recycling world. Plate tectonics began to drag slabs of crust back into the mantle through deep subduction zones. Over hundreds of millions of years, entire regions of ocean floor and even the edges of continents were swallowed, reheated, and transformed, leaving little direct trace at the surface. What happens to a continent that is pulled into the interior and melted beyond recognition? Yet not everything vanished. Scientists have found that the oldest surviving pieces of continental crust, called cratons, are like armored relics. These regions, such as parts of Western Australia and South Africa, contain rocks more than 3 billion years old. They form strong, thick keels that resisted destruction and preserved tiny windows into pre-Pangea worlds. Imagine standing on one of the first true continents during this time. The ground would shake from constant mega eruptions. Rivers of lava would cut across the landscape, and the air would burn the lungs. Overhead, meteor firestorms would tear through the sky, turning night into blinding flashes. Compared with this, the age of dinosaurs would seem almost calm. Given such relentless destruction, how can anything be known about continents that no longer exist on any map? The answer comes from some of the smallest survivors on Earth, microscopic zircon crystals. Locked inside these durable minerals are chemical memories of vanished crust, silent records of lands erased from the surface, but still speaking through their ancient atoms. Those crystals are not the only survivors. Deep beneath the familiar outlines of modern continents lie far larger ghosts, ancient cratons. These are the oldest, most stable cores of continents, thick and buoyant blocks of rock that have endured billions of years of tectonic violence. They form the hidden hearts of regions like the Kapval Craton in southern Africa, the Pilbara in Western Australia, and the Canadian Shield, where strong ancient rocks come close to the surface. For millions of years, these cratons have ridden the shifting plates like armored rafts. Their roots plunge more than 150 kilometers into the mantle, making them difficult to break and almost impossible to recycle completely. Scientists have mapped their ages, rock types, and deformation patterns, tracing scars from collisions and rifts frozen into their bones. When these patterns are compared from continent to continent, many cratons match one another in surprising ways, powerful evidence showing that they were once welded together in earlier supercontinents. Cratons provide the big framework, but zircons give the fine print. Zircons are tiny crystals of zirconium silicate that grow inside igneous rocks. They are incredibly durable, surviving erosion, transport, burial, even partial melting, while still preserving their internal structure. Inside each crystal, radioactive elements like uranium decay into lead at a precise rate, creating atomic clocks that can be read billions of years later. At the same time, trace elements and isotopes record the chemistry of the magma and the environment where the crystal first formed. Some of these zircons are among the oldest known materials on Earth. Grains from the Jack Hills of Western Australia are over 4.3 billion years old, older than any intact rock on the planet. Their chemistry indicates that they crystallized from magmas interacting with continental crust, not just simple oceanic basalt. Even more striking, certain oxygen isotope ratios suggest that liquid water was present at the surface when these crystals formed. How could continental crust and stable oceans exist at a time when Earth is often imagined as a fiery, hellish world? These zircons are one of the most important clues that early continents rose, eroded, and vanished long before any familiar map. Another line of evidence comes from paleomagnetism. When volcanic rocks cool, or fine sediments settle and harden, iron-bearing minerals inside them align with Earth's magnetic field, like microscopic compass needles. As the rock solidifies, that alignment is locked in, preserving both the direction and the inclination of the field at that latitude. Many millions of years ago, these tiny magnets recorded where the rock sat on the globe and whether the field had normal or reversed polarity at that time. Scientists have collected paleomagnetic measurements from cratons in Africa, Australia, India, and beyond. By comparing these magnetic signatures through time, they can reconstruct the approximate positions and motions of ancient continental fragments. In many cases, Paths from different cratons line up, overlap, or curve together in ways that only make sense if they were once joined in larger landmasses. No coastlines remain, no fossils mark those vanished shores, yet the magnetism frozen in old rocks still traces their journeys. Together, cratons, zircons, and paleomagnetism turn early Earth into a detective story. There are no direct maps, only scattered clues in minerals, magnetism, and rock chemistry. When researchers overlay these independent lines of evidence, a striking pattern emerges. The scars in South Africa's Kapval Craton and Western Australia's Pilbara Craton line up in age, style, and magnetic history. Linked, they outline what may be Earth's first true supercontinent, a vanished landmass with a name that hints at its dual origin, Vialbara. What did this ancient continent look like, and how did it shape the world that would one day allow dinosaurs to rise? To answer that, the story must travel even deeper into time, to a planet still finding its balance between fire and ocean. From that blazing backdrop, Vialbara steps into view as one of the most mysterious characters in Earth's early history. Long before Pangea, between about 3.6 and 2.7 billion years ago, this hypothesized supercontinent may have gathered scattered island arcs into a single powerful mass of rock. If real, it would be one of the most ancient large land masses scientists have ever tried to reconstruct. The name Vialbara joins two anchors on opposite sides of the Indian Ocean, the Kapval Craton in southern Africa and the Pilbara Craton in Western Australia. Each is a block of ancient continental crust, like a fossil backbone from the Archean Eon. Their rocks share strikingly similar ages, internal structures, and volcanic layers, as if they were once pages from the same torn book that have drifted apart by thousands of kilometers. Scientists have found evidence showing that both cratons recorded the same style of greenstone belt volcanism. These belts preserve thick piles of basaltic lava, volcanic ash, and sediments laid down in long, narrow troughs. In both Kapval and Pilbara, the belts show nearly matching sequences: submarine lava flows, chemical sediments rich in iron, and later intrusions of granite-like magmas. The timing of these events lines up within tens of millions of years, suggesting that the two regions felt the same pulses of deep Earth activity. Sedimentation patterns tell a similar story. River and shallow marine deposits in Kapval and Pilbara shift in the same way from deeper to shallower environments, then are deformed by comparable tectonic events. There is evidence showing that mountain building, basin subsidence, and later erosion happened at overlapping times in both places. To many researchers, this parallel history is too strong to be a coincidence. Paleomagnetic data add another, more precise line of argument. Tiny magnetic minerals inside these ancient rocks locked in the direction of Earth's magnetic field when they formed. When scientists measure these signals, they can estimate the ancient latitude and orientation of each craton. During key intervals of the Archean, the magnetic directions from Kapval and Pilbara point to the same general latitudes and relative positions, reinforcing the idea that they once formed the core of a single, larger supercontinent. Yet Vialbara's surface would hardly resemble any familiar continent. Low, dark proto-continents rose only slightly above vast, iron-rich oceans that stained the water a deep, rusty color. The sky was heavy with methane and carbon dioxide, with almost no free oxygen. Constant volcanic outgassing pumped sulfur and greenhouse gases into the atmosphere, and asteroid impacts still scarred the young crust. In this harsh environment, early microbial life clung to shorelines and hydrothermal systems, while the land itself remained mostly barren rock. Despite this growing picture, Vialbara remains controversial. Some scientists argue that Kapval and Pilbara were tightly joined in a coherent supercontinent. Others suggest a looser chain of microcontinents and island arcs that drifted in the same hemisphere but never formed a single stable block. In such deep time, even basic outlines are contested, and small changes in data can transform entire maps. Vialbara matters because it may represent one of the most important early experiments in building large, stable continents. Its thick, buoyant crust could have played an important role in sheltering the first ecosystems from intense ultraviolet radiation and violent ocean chemistry. If these protocontinents endured, they created footholds where shallow seas, tidal flats, and volcanic shorelines could nurture microbial mats that slowly altered the atmosphere. And Valbara was likely not alone. As its cratons assembled and drifted, another ancient landmass, called Ur, may have been taking shape on the far side of the planet. While Valbara's fate was to vanish almost without a trace, Ur would become one of the most long-lived continents in Earth's history, surviving through multiple supercontinent cycles and helping to shape the world that, many millions of years later, would belong to dinosaurs. As Valbara rose and fell, Ur emerged on the other side of the planet as a different kind of survivor. Forming perhaps around 3 billion years ago, it was one of the earliest proposed true continents, a stable block of crust that would outlast ocean basins, mountain ranges, and entire supercontinents. It did not remain whole forever, but its fragments may still lie hidden beneath familiar landscapes. Scientists have evidence showing that the ancient cores of India, Western Australia, and parts of Africa contain rocks far older than the continents around them. These ancient cratons, made of hard, buoyant crust, appear like buried anchors inside younger land. Radiometric dates, magnetic signatures, and chemical fingerprints suggest that several of these cores were once welded together as Ur, before being stitched into other continents during later collisions. Compared with the giant supercontinents that came later, Ur was probably modest in size. It may have been ringed by small volcanic islands and narrow, shallow seas rather than spanning a hemisphere. Yet its crust was thick and strong. This buoyant foundation helped it float high on the mantle, while other early landmasses were dragged down and recycled. In a world where most crust was temporary, Ur became one of the most persistent building blocks of Earth's surface. To see how this ancient land connects to the present, imagine a single grain of sand on a beach in eastern India. It lies in the surf today, rolled back and forth by waves, surrounded by modern cities and a very different environment. Trace that grain back through millions of years, and it might have been part of a riverbed, then a buried sandstone, then a mountain crushed in a continental collision. Continue further, and its parent rock could once have formed deep inside Ur itself, carried across the globe as plates shifted and supercontinents assembled and broke apart long before Pangea. Over time, Ur likely played an important role in several great continental experiments. Scientists have proposed that it was folded into the early supercontinent Kenorland, then later into Columbia, also called Nuna, and again into Rodinia. Each time, its ancient cores were locked against other cratons, forming the interior of new landmasses that reshaped oceans, climate, and eventually, the conditions that would allow life to expand and dinosaurs to rule many millions of years later. Yet even this survivor continent was far from safe. The young Earth was bombarded by large impacts and shaken by powerful tectonic forces. Vast volcanic provinces may have flooded parts of Ur with lava. The sun was dimmer, but the atmosphere lacked a strong ozone layer and almost all breathable oxygen, so intense radiation bathed its bare rocks and early microbial mats. What would it have been like to stand on such a shore, under a coppery sky, with no plants, no animals, and no protection? Ur shows that a continent can vanish as a single named entity, while its pieces continue inside modern landmasses. Its identity disappeared, but its rocks did not. In this way, vanished without a trace often means that the map is gone, not the material itself. As Ur and the remnants of Valbara evolved, Earth was preparing for something even larger, the assembly of one of the first truly global supercontinents, known as Kenorland. As Earth's early fragments merged, that preparation reached a climax in a landmass both vast and strange. This was Kenorland, one of the most ancient supercontinents that scientists can reconstruct with confidence. It formed around 2.7 to 2.5 billion years ago, when scattered cratons that would one day help build North America, Scandinavia, and Australia locked together into a single powerful block of rock. At the time, the planet's surface looked nothing like the familiar maps of later eras. The Canadian Shield, the Baltic Shield, and old Australian cratons were not distant regions separated by oceans. They were neighbors along the same rugged coastline. Some fragments that once belonged to Ur may also have been stitched into this early giant, turning Kenorland into a broad, irregular cap on a still restless world. How can scientists be so sure that these far-flung pieces once fit together? The answer lies in the rocks themselves. Long belts of volcanic and sedimentary rocks of the same age and composition run across these cratons like matching scars. Paleomagnetic minerals locked inside them preserve ancient directions of Earth's magnetic field, and there is strong evidence showing that these directions line up when the blocks are rotated and pushed together. The result is a coherent outline of a vanished continent. Kenorland's environment was harsh and dramatic. Much of its interior may have been a high volcanic plateau, built from repeated eruptions that spilled dark lava across the land. Along its edges, shallow seas flooded low-lying margins, forming broad continental shelves where early microbial mats spread over mud and sand. Above all of this hung a sky almost without oxygen, thick with methane, carbon dioxide, and other greenhouse gases. To the tiny life forms of that time, this was normal. Yet that normal world was about to face one of the most profound shocks in Earth's history. Photosynthetic microbes living in those shallow seas began releasing oxygen as a waste product, and over many millions of years, this gas started to accumulate. The event that followed, known as the Great Oxidation Event, transformed the atmosphere from a reducing blanket into something far more reactive. For many existing microbes, oxygen was toxic. Their familiar environment turned deadly. Kenorland itself may have played an important role in triggering this crisis. As the supercontinent rose and weathered under intense rain and wind, its exposed rocks reacted with carbon dioxide and drew it out of the air. With greenhouse gases reduced, global temperatures dropped. Evidence from ancient sediments suggests that ice sheets advanced toward the equator, perhaps producing some of the earliest snowball-style glaciations. A once warm world may have frozen almost solid. At the same time, Kenorland was beginning to break apart. Rifts opened across its interior, volcanoes tore through thinning crust, and new ocean basins formed between the separating blocks. Seafloor spreading accelerated, carrying the fragments away and recycling older crust back into the mantle. The supercontinent dissolved into smaller pieces that would later be reorganized into new assemblies. For early life, this combination of rising oxygen, violent volcanism, and severe climate swings was one of the most extreme environmental crises the biosphere had ever faced. Many lineages likely vanished, while others adapted to oxygen and cold, setting the stage for more complex ecosystems. In this way, Kenorland's rise and fall did more than reshape the map. It altered the chemistry of the entire planet. The pattern that began with Kenorland would not be the last. In the billions of years that followed, other supercontinents such as Columbia, Rodinia, and finally Pangea would form, change the climate, and then tear themselves apart. Each cycle opened new oceans, closed old ones, and forced life to adapt or die. What new worlds did these later giants create, and how did they prepare the stage for the age of dinosaurs? When Kenorland vanished, Earth did not simply return to scattered islands. Many millions of years later, the planet assembled something even larger and more unified. Geologists call it Columbia or Nuna, and it may have been one of the most expansive supercontinents ever to exist. Columbia seems to have dominated the globe between about 1.8 and 1.3 billion years ago. During this time, most of the world's continental crust was welded into a single sprawling landmass that stretched for thousands of kilometers from pole to pole. What is striking is not only its size, but how many familiar pieces of the modern world were already present, locked together in a very different arrangement. Scientists have evidence showing that ancient cratons from North America, South America, Baltica, Siberia, India, Australia, and perhaps parts of Antarctica once formed the backbone of Columbia. Blocks that are now separated by whole oceans stood edge to edge, their roots fused deep into the lithosphere. To reconstruct this hidden geography, researchers must treat each craton like a fragment of a shattered map. The clues do not come from fossils or dinosaur bones, but from the rocks themselves. Long mountain belts in North America line up precisely with matching belts in Greenland and Baltica when the continents are reassembled. The ages of metamorphism and magmatism in these belts also match, showing that the same collision zones once ran continuously across Columbia. Paleomagnetic measurements provide further evidence, revealing that separated cratons recorded similar magnetic pole positions at the same time, meaning they once shared latitudes and moved together as a single body. On the surface, Columbia's interior was probably a vast, low-relief landscape. Earlier mountain chains had been worn down by hundreds of millions of years of erosion, leaving broad, stable cratonic plains under a sun that was still slowly brightening. Rivers crossed wide plateaus, shallow seas flooded some margins, and the atmosphere changed only gradually. This long interval is sometimes called Earth's boring billion because the surface environment appears relatively stable. But inside the planet, nothing was boring. Mantle convection continued to churn, and heat from the deep interior built up beneath the insulating lid of the supercontinent. Columbia's enormous size likely altered flow patterns in the mantle, concentrating hot material beneath the thickest parts of the lithosphere. This hidden heat played an important role in weakening the crust and priming it for future rifting. What happens when such a massive landmass finally destabilizes? As stress and heat rise, giant rift systems can tear continents apart. Vast eruptions of flood basalt may pour out from deep fractures, releasing gases that can drive dramatic climate and sea level changes. New oceans open where solid rock once stood, and coastlines race across the globe. Columbia did not survive this internal pressure. Over tens of millions of years, it fragmented into drifting continents that wandered across the planet. Yet the story did not end there. Those fragments would later collide again, assembling another supercontinent, Rodinia, whose eventual breakup may have helped trigger some of the most extreme ice ages in Earth's history. As Columbia's fragments drifted apart, Earth's restless plates began a new slow-motion collision. Over many millions of years, scattered cratons slammed together again, welding into a fresh, giant landmass. This new supercontinent would dominate the planet's surface and climate. Its name was Rodinia. Rodinia probably formed around 1.1 billion years ago and lasted until roughly 750 to 600 million years ago. Many of the same ancient blocks that once belonged to Columbia were gathered again, but in a different pattern. Scientists have evidence showing that Laurentia, the ancient core of North America, sat near the center of this vast continent, like a hub in a stone wheel. Around it, other cratons such as Amazonia, Baltica, Siberia, and Australia locked into place, building a landmass thousands of kilometers across. Yet Rodinia's exact outline remains one of the most debated puzzles in geology. The supercontinent left no clear coastlines, only scattered mountain belts and altered rocks. Paleomagnetic signatures in ancient minerals record where those rocks once sat relative to Earth's magnetic field, but the signal is faint and often disturbed. Different teams of scientists use the same limited structural and magnetic evidence to draw very different maps. Did Australia lie snug against Western Laurentia? Or was it Siberia instead? Were some blocks rotated or even flipped? Each reconstruction tells a slightly different story. Whatever its precise shape, Rodinia's environment would have been extreme. With so much land fused together, The interior lay far from the moderating influence of oceans. Vast central regions likely baked under arid climates, with strong temperature swings between scorching days and cold nights. In contrast, the long coastlines faced powerful monsoon systems. Seasonal winds would have driven heavy rains onto some margins, while offshore, nutrient-rich upwelling turned nearby seas into fertile plankton-filled waters. Rodinia's breakup may have played an important role in pushing Earth into crisis. As the supercontinent began to rift apart around 750 million years ago, new ocean basins opened and chains of volcanoes flared to life along the fresh margins. Volcanic outgassing changed the balance of atmospheric carbon dioxide, while the exposure of young, weatherable rock drew CO2 out of the air. Many scientists link this shifting chemical balance to the Neoproterozoic snowball Earth events, when runaway glaciations may have frozen oceans nearly to the equator. Imagine that world. Ice sheets extend across continents, burying mountains. Sea ice locks the oceans beneath a bright, reflective shell that bounces sunlight back into space. Temperatures plunge. Survival for early multicellular life becomes a planet-wide struggle, confined to thin refuges of liquid water beneath the ice or near volcanic warmth. Yet this frozen catastrophe also reset the planet. When the global or near-global ice finally melted, torrents of meltwater and intense weathering flooded the oceans with nutrients. Algae and microbes boomed. Food webs thickened. This chemical windfall may have fueled evolutionary innovation and prepared the way for the later Cambrian explosion, when animal life diversified with new bodies, hard parts, and complex behaviors. In this sense, Rodinia's destruction was not only geological, it was biological. The rise and fall of a supercontinent helped rewrite the rules of life on Earth, shaping the oceans and climates that would, much later, support forests, reptiles, and eventually the dinosaurs that ruled the Mesozoic world. As Rodinia's broken fragments drifted apart, Earth prepared an even larger stage. Many millions of years later, in the southern half of the planet, those fragments would collide again to form a new giant, Gondwana. This supercontinent stretched from pole to subtropics and united lands that are now South America, Africa, Antarctica, Australia, the Indian subcontinent, and the Arabian Peninsula into one of the most extensive landmasses in Earth's history. Scientists have strong evidence showing that these distant regions were once joined edge to edge. Identical fossil plants, such as the seed fern Glossopteris, appear in rocks from Brazil, South Africa, India, and Antarctica. Glacial scratches and thick deposits of ancient ice-carved debris line up across these continents, forming continuous belts that only make sense when the pieces are locked back together over the South Pole. Even long mountain chains, broken apart by oceans, match in rock type and age across the Atlantic, revealing the old seams of Gondwana. During the Paleozoic era, Gondwana's landscapes changed in dramatic cycles. At times, especially in the late Paleozoic, vast ice sheets spread over high plateaus and lowlands, turning much of the south into a frozen desert of grinding ice and rock. Later, as climates warmed, broad lowlands flooded with rivers and swamps. Dense forests and thick mats of plants grew in humid basins, forming the coal layers that are mined on several continents today. Shallow seas covered wide areas of its margins, filled with trilobites, early fish, and shelled creatures that left countless fossils in the seafloor sediments. These environments hosted some of the earliest complex animal ecosystems on land and in the water. Along shorelines and river plains, the first land plants spread, stabilizing soils and changing the atmosphere. In nearby seas, jawed fish and armored fish hunted among reefs, while trilobites crawled over the seafloor. On floodplains, early four-limbed vertebrates began to leave the water. In this way, Gondwana played an important role as a cradle for ecosystems that would, step by step, evolve into the forests, river systems, and coastal plains that later supported dinosaurs. Gondwana's size and position also shaped global danger. When it lay across the South Pole, its strong influence on ocean currents and climate may have contributed to major environmental crises, including the late Ordovician and the devastating Permian mass extinctions. Changes in ice cover, sea level, and volcanic gases linked to this supercontinent helped push many species to the edge. By the time dinosaurs first appeared in the Triassic, the crust beneath their feet already carried this deep history. Early dinosaurs walked across rifted valleys and broad uplands that had once been connected ice fields and coal swamps of Gondwana, even as the supercontinent itself was in motion, merging northward into Pangea. That motion came with power and danger. As Gondwana began to fracture again, great rift systems tore through its interior. In some regions, such as southern Africa and Antarctica, the Karoo-Ferrar Large Igneous Province erupted, flooding huge areas with lava and releasing gases that reshaped climates and habitats. These volcanic events altered ecosystems, opening and closing paths for reptiles and early dinosaurs as new deserts, highlands, and coastlines formed. To understand the world that later apex predators inherited, it is necessary to understand Gondwana. This southern giant existed before Pangea, guided climates, steered extinctions, and built the foundations of dinosaur environments. Its shattered pieces still form much of the southern hemisphere today, silent reminders of a lost supercontinent beneath the dinosaurs' feet. Those silent fragments tell a darker story. For millions of years, continents have not only formed and drifted, they have also been torn apart, thinned, and dragged back into the deep earth. A supercontinent can seem permanent on human timescales, but in geological time, it is only a temporary arrangement in a dangerous, moving environment. Continents float on the mantle because their crust is thick and relatively light, yet they are not indestructible. Under the right conditions, even strong continental plates can be stretched until they crack. When hot mantle begins to rise beneath a continent, it heats and weakens the lower lithosphere. The surface responds by sagging and splitting, forming long rift valleys. Over millions of years, those valleys can widen, fill with water, and become new ocean basins, slicing a once continuous landmass into scattered pieces. Scientists have evidence showing that this process, called rifting, played an important role in the breakup of Pangea. The Atlantic Ocean began as a series of rifts that opened between North America, Africa, and Europe. Similar scars can be traced back through time to earlier supercontinents such as Rodinia and Gondwana. Each time, the same basic pattern repeats: stretching, faulting, volcanic activity, and finally, the birth of an ocean that separates former neighbors. But rifting is only one of the most visible ways a continent can die. At convergent boundaries, where plates collide and one is forced beneath another, parts of continents can be shaved away and lost. This subduction erosion occurs when the edge of a continent is scraped, fractured, and carried downward with the descending slab. In other cases, dense lower roots of continental lithosphere detach in a process called delamination. Once separated, these deep blocks sink into the mantle and melt, removing volume and buoyancy from the overlying continent. Mantle plumes add a more violent threat. These are powerful upwellings of unusually hot rock that rise from deep within the planet. When a plume head reaches the base of a continent, it can trigger enormous volcanic outpourings known as large igneous provinces. Lava floods across the surface, sometimes covering regions the size of modern continents in a geologically brief moment. The Central Atlantic Magmatic Province, active during the breakup of Pangea, produced such intense volcanism that it is linked to mass extinction. Earlier supercontinents show similar patterns. Large igneous provinces tied to Rodinia and Gondwana erupted many millions of years ago, weakening their interiors and helping initiate rifting. These events were planetary-scale natural disasters, releasing gases that disrupted climate and oceans. Over deep time, erosion then grinds down the lava plateaus, mountain ranges sink, and oceans close again at new subduction zones. The result is that whole coastlines vanish, and even the outlines of former continents are erased. Only resistant cratonic cores, scattered mineral grains, and subtle geophysical anomalies remain. When a continent is said to have vanished, it means its once coherent shape has been destroyed, its rocks scattered across distant plates or pulled deep into Earth's interior, leaving only traces for scientists to uncover. Yet even a vanished continent can still be hiding in plain sight. One of the most striking examples is Zealandia, a ghostly landmass draped across the southwest Pacific. On modern maps, it appears only as New Zealand, New Caledonia, and a scattering of small islands. But beneath the waves lies a block of continental crust, roughly half the size of Australia. Its broad plateaus and ridges drowned under kilometers of cold ocean water. Scientists have assembled a detailed picture of this hidden continent using seismic surveys, rock samples, and the shape of the seafloor. There is strong evidence showing that Zealandia rifted away from Antarctica and eastern Australia many millions of years ago, as the great southern continent of Gondwana began to fragment. As the crust stretched and thinned, it slowly subsided. What had once been highlands and coastal plains slipped below sea level, leaving only the highest fragments as lonely islands in a vast marine environment. Drilling into the submerged plateaus has brought up fossils of shallow water organisms and continental rocks, proving that this region was once dry land. Sediments show ancient rivers, coastal forests, and ecosystems that later vanished beneath rising seas. In this way, Zealandia demonstrates that a continent does not need to sink into the mantle to disappear from view. It can simply be thinned, flooded, and concealed, its broad outlines erased, while its deeper crust still survives. On the opposite side of the world, another lost continent met a far more violent fate. Greater Adria was a continental fragment that once lay between Africa and Europe, a microcontinent with its own coastlines, sedimentary basins, and mountain ranges. As the African plate moved north, Greater Adria was driven into the underside of southern Europe. The collision was anything but gentle. Rocks were scraped off, folded, and crushed, while most of the continental body was dragged downward into subduction zones. Today, only scraps of Greater Adria remain, welded into powerful mountain belts such as the Alps, Apennines, and Dinarides. Deep beneath them, seismic imaging has revealed thick slabs of former continental material sinking into the mantle. This is continental destruction in action. Plates grinding together, crustal blocks shattered, entire regions pulled under like a ship in a storm. What seems solid and permanent on a human timescale proves fragile when viewed across hundreds of millions of years. These two examples show that continental crust can be stretched, submerged, and even consumed. Geophysicists have also detected other anomalous regions of thick crust and unusual mantle structure beneath oceans, hinting at additional lost fragments scattered around the globe. If such dramatic changes can occur in only tens or hundreds of millions of years, what could repeated cycles of collision and breakup do over billions of years? The answer is simple and unsettling. Almost every trace of far older continents could be erased. The existence of Zealandia and Greater Adria proves a crucial point. Vanished continents are not science fiction. They are a natural consequence of how Earth works. If the surface can be wiped almost clean, the question becomes unavoidable. Where did all that ancient continental material go? The answer lies far below the last surviving mountains in a hidden archive inside Earth's mantle. For millions of years, sinking slabs and peeling continental roots have been dragged downward, and parts of them have survived. They no longer form coastlines, but they still leave powerful marks. When continents are subducted or their deep roots are stripped away, not every fragment melts and disappears. Dense blocks of rock can plunge thousands of kilometers down and linger there for billions of years. Scientists have shown that these buried remnants keep their own physical and chemical identities, like ghost continents folded into the mantle. They cannot be seen directly, but they change how waves from earthquakes move through the planet. Using seismic tomography, scientists turn global earthquakes into a kind of planetary X-ray. Waves race through some regions, slow down in others, and together they create a three-dimensional picture of Earth's interior. One of the most striking discoveries is the presence of two giant structures resting near the base of the mantle, under Africa and the Pacific. These are the African and Pacific Large Low Shear Velocity Provinces, or LLSVPs, where shear waves move unusually slowly. These LLSVPs appear as vast, dense piles, thousands of kilometers wide and hundreds of kilometers tall. What are they made of? One idea is that they are graveyards of ancient oceanic plates and continental fragments gradually collected over many millions of years. In this view, pieces of supercontinents older than Pangea, maybe even from Valbara or Ur, could be locked inside these deep reservoirs, still influencing the mantle long after their surfaces vanished. The mantle's memory is also written in chemistry. Certain volcanic rocks, such as some ocean island basalts from places like Hawaii and Iceland, contain unusual isotopic signatures. These patterns in elements like helium, neodymium, and lead are evidence showing that their source regions include very old, recycled crust. Some signatures point back to material that formed early in Earth's history, long before dinosaurs, and even before complex fossils. These chemical anomalies act like DNA traces from lost continents. They reveal that fragments of long-destroyed crust still feed modern volcanoes and help drive mantle plumes. When these plumes tap into deep, compositionally distinct reservoirs, the results can be dramatic. They can fuel one of the most destructive geological events on the planet. Massive flood basalt eruptions that cover continents in lava, release huge volumes of gas, and disrupt the global environment. Events like these have played an important role in reshaping climate, oceans, and life. Even if ancient continents cannot be mapped on the surface, their buried remains still help steer plate motions, focus hotspots, and control where and when such dangerous outbursts occur. The rocks remember. And in the next chapter of the story, life remembers too, because the rise and fall of these hidden lands created and destroyed habitats, guiding evolution along the winding path that would one day lead to dinosaurs. Life remembers through survival and extinction. Every time the continents gather into a single giant landmass and then tear apart again, the entire planet's environment is rewritten. Ocean currents are redirected, winds change course, coastlines appear and vanish. For living things, each supercontinent is both a powerful opportunity and a deadly trap. The earliest attempts at continents, such as Valbara and the slightly younger Ur, rose from a world ocean many millions of years before the first animals. These were not quiet places. Volcanic arcs and impact scars marked their surfaces, but their presence changed everything for early life. As rain and chemical weathering attacked these new rocks, nutrients like phosphorus and iron washed into nearby shallow seas. Scientists have found evidence showing that these flooded continental margins supported stable microbial mats and layered stromatolites, some of the first long-lasting ecosystems on Earth. As continents grew and merged into larger blocks like Kenorland, the stakes increased. Wide areas of exposed rock meant more weathering, and that process drew down greenhouse gases such as carbon dioxide. At the same time, it delivered a constant supply of nutrients to coastal waters, feeding photosynthetic microbes that released oxygen as a waste product. This slow geologic feedback helped trigger the Great Oxidation Event about 2.4 billion years ago, one of the most dramatic atmospheric changes in Earth history. For many organisms, rising oxygen was a catastrophe. Minerals that had been stable suddenly rusted, and methane, a strong greenhouse gas, was destroyed, sending the climate into severe swings. Mass die-offs of oxygen-sensitive microbes followed. Yet this crisis also cleared the way for new metabolic pathways and more energetic forms of life. The arrangement of Kenorland's landmasses and their relentless erosion played an important role in turning the sky from poisonous to breathable. Later, the supercontinent Rodinia set the stage for an even more extreme test. As Rodinia broke apart around 750 to 600 million years ago, rifting and new ocean basins changed how heat and salt moved through the seas. Many models suggest that this configuration helped plunge Earth into snowball conditions, with ice possibly reaching near the equator. Glaciers scraped continental surfaces bare, sea levels fell, and early multicellular organisms were pushed to survival in a few ice-free refuges. It was one of the most severe bottlenecks life has ever faced. Yet when the ice retreated, freshly ground rock again pumped nutrients into the oceans. Complex algae and soft-bodied animals spread through rejuvenated continental shelves. Scientists have found fossils of these Ediacaran creatures on several former pieces of Rodinia, showing how a frozen world gave way to a burst of experimentation. The assembly of Gondwana during the late Precambrian and early Paleozoic continued this pattern of danger and opportunity. Its vast southern bulk influenced global winds and ocean circulation, encouraging repeated glaciations that reshaped marine habitats. In cold intervals, ice sheets locked up water and sea levels dropped, exposing continental shelves and wiping out shallow marine communities. In warmer times, rising seas flooded low-lying Gondwanan margins, creating broad, sunlit platforms that supported dense reefs, trilobites, and early vertebrates. On land, Gondwana's long, humid coastal belts and interior basins helped early plants take root. Simple moss-like vegetation and later forests spread across its river systems, pulling carbon dioxide from the air and stabilizing soils. This living cover altered weathering rates and nutrient delivery, feeding richer coastal seas. Food webs became more complex, with jawed fishes and early tetrapods evolving in environments strongly controlled by Gondwana's size and position. Across all these cycles, from Valbara to Gondwana, supercontinent assembly and breakup acted as one of the most powerful engines of macroevolution. Each collision raised mountain chains that bled nutrients into the sea. Each rift opened new coastlines and isolated basins. Ocean gateways opened and closed, turning warm currents on and off like planetary switches. With every reconfiguration, climates lurched, sea levels rose and fell, and habitats were created, squeezed, or erased. For life, each tectonic reshuffle was a roll of the dice. Some lineages adapted to new coastlines, new temperatures, and new chemical conditions, diversifying into unfamiliar niches. Others were trapped by cooling seas, suffocating oceans, or poisonous volcanic gases. Many vanished forever, their existence known only from rare fossils and subtle chemical traces. By the time Pangea finally formed around 335 million years ago, it inherited a biosphere already filtered by billions of years of continental experiments. The survivors were those that had weathered snowball Earth, oxygen shocks, and shifting Gondwanan climates. Their bodies, senses, and behaviors had been tuned by repeated crises. In this pre-Pangean forge, the foundations were laid for amphibians that would become reptiles, reptiles that would become archosaurs, and archosaurs that would later give rise to the most dangerous dinosaurs that ever existed. Those survivors did not step into a blank new world. They carried the legacy of continents that had formed and vanished many millions of years before the first recognizable dinosaur ever left a footprint. From Valbara and Ur, through Kenorland, Columbia or Nuna, Rodinia, and finally Gondwana, Earth had already built and broken supercontinents again and again. Each of these ancient worlds changed the planet in powerful ways. When supercontinents came together, mountains rose, volcanoes erupted, and oceans closed. When they split apart, new coastlines formed, shallow seas spread, and climates shifted. Scientists have found evidence showing that these cycles drove long pulses of oxygen change glaciation, and extinction. Every rearrangement reshaped the environments in which early life struggled, adapted, and evolved. By the late Paleozoic, the assembly of Pangea was simply the latest turn in this deep time pattern. Gondwana, already one of the most massive landmasses on Earth, moved toward a set of northern continents that would become Laurasia. Between them, long subduction zones consumed ancient ocean crust, welding the pieces together in one of the most complete supercontinents in Earth's history. Where continents collided, strong mountain belts rose, such as the ancestors of the Appalachians and Urals. Beneath the surface, however, Pangea was a geological patchwork. Its crust was built from ancient cratons that once formed the hearts of Valbara, Ural, and other lost continents. These old blocks, more than 2 or 3 billion years in age, were stitched together by younger volcanic arcs and collision zones. In a single cross-section of rock, scientists can sometimes trace this story. Deep, stable roots from vanished worlds, overlain by folded sediments and igneous rocks from more recent continental impacts. This hidden architecture controlled how Pangea behaved. The shape of its coasts, the depth of its inland basins, and the height of its mountains all influenced wind patterns, ocean currents, and rainfall. The early Mesozoic atmosphere, with its changing levels of carbon dioxide and oxygen, was not random. It was the inherited outcome of billions of years of tectonic rearrangements, flood basalts, and buried organic carbon that earlier supercontinents had produced. In this inherited environment, the first true dinosaurs would later find both opportunity and danger. The same forces that built Pangea also primed it for catastrophic failure. Heat trapped beneath the thick supercontinent crust made it unstable. Tension lines formed, rifts opened, and massive volcanic provinces prepared to erupt. When these flood basalts poured out, they released gases that could drive rapid warming, acid rain, and ocean stress. How would even the strongest dinosaurs cope with such violent changes? Scientists have gathered evidence showing that the dinosaur world was only the latest act in a much longer planetary drama. Pre-Pangea continents played an important role in setting the stage, dictating where seas would lie, where forests could grow, and where archosaurs could spread. In the rest of this series, the focus turns to Pangea itself, how it formed, how it began to tear apart, and how those events guided the rise, spread, and eventual extinction of the dinosaurs. Because just as Valbara, Ur, and Rodinia vanished without a trace on the surface, the dinosaurs' world would also be shattered. Its continents would be ripped open, its ecosystems broken, leaving only scattered fossils and fragmented crust to whisper what was lost. The supercontinent that empowered the most dangerous dinosaurs would also help destroy them. What happened when their world finally cracked? When that later dinosaur world finally cracked, it was repeating a pattern that had begun far earlier in Earth's history. Many millions of years before any dinosaur left teeth or bones in the rock record, another giant landmass came together and changed the planet in ways that can still be traced today. That ancient continent is called Canorland. Canorland formed in the late Archean to early Proterozoic, more than 2.5 billion years ago. It was younger than Valbara and Ur, but still unimaginably old compared with the age of the dinosaurs. Instead of forests and herds, its surface held bare rock, simple microbial life, and strange chemical seas. Yet this silent supercontinent played an important role in turning a violent young planet into a more stable, habitable world. Scientists have defined Canorland as one of the first supercontinents that can be reconstructed with some confidence. The key pieces are ancient cratons, the strong inner cores of continents that resist destruction. Parts of modern North America, Baltica in northern Europe, Western Australia, and the Kalahari region of southern Africa all preserve these old fragments. When their shapes, rock ages, and magnetic directions are compared, they appear to fit together into a single, broad configuration, the lost outline of Canorland. The evidence showing that these scattered blocks were once neighbors comes from several independent clues. Greenstone belts, ancient volcanic and sedimentary rocks, line up in pattern and chemistry across different cratons, as if once part of the same long mountain chains. Granites in Canada and Scandinavia share similar ages with granites in Western Australia and Kalahari, recording pulses of continental collision at the same time. Paleomagnetic measurements, frozen into iron-bearing minerals when the rocks formed, reveal matching directions and latitudes, indicating that these regions once sat side by side on a single, larger landmass. Kenorland matters because it represents one of the most important transitions in Earth history. For the first time, large portions of Earth's crust locked together into a long-lived, semi-stable continent. This thicker, stronger crust could rise higher above sea level, supporting broad plateaus and wide, shallow continental seas around its margins. Those shallow seas became chemical laboratories, where weathered minerals, dissolved gases, and microbial life interacted over millions of years. With more stable continents, erosion and weathering intensified, pulling elements like carbon, phosphorus, and sulfur from the rocks and washing them into the oceans. This strengthened the planet's surface chemical cycles and helped regulate temperature and ocean chemistry. Could such changes in the environment have set the stage for later explosions of complex life? Many scientists see Kenorland's assembly as a crucial step toward a more balanced, life-friendly Earth. There is also evidence showing that the assembly and eventual breakup of Kenorland dramatically altered the atmosphere and oceans. As volcanic belts and rift zones opened and closed, they released and removed greenhouse gases, while microbial life responded to new habitats and nutrient flows. Some models link the destruction of Kenorland to one of the most severe ice ages in Earth's history. When frozen oceans may have reached the equator, how could the birth and death of a continent plunge the planet into near-global ice? And what did that mean for the distant future world of the dinosaurs? For hundreds of millions of years at a time, continents do not rest. They drift like armored plates in a slow planetary war, grinding, colliding, and tearing apart while the oceans and atmosphere react above. Deep inside Earth, hot mantle rock circulates, and this convection, together with slab pull from sinking oceanic crust and ridge push from mid-ocean ridges, drives the rigid plates that carry entire continents. When continents meet, the impact is slow, but the damage is immense. Instead of shattering, their buoyant crust crumples and thickens, building long mountain belts that can stretch for thousands of kilometers. Rocks are folded, buried, and heated, and separate landmasses are welded into a single body. The scars of this collision remain locked in the crust as hidden battle lines long after the surface mountains have worn down. Kenorland formed in this way. Many millions of years ago, smaller protocontinents drifted across ancient oceans and rammed together again and again. Each collision raised powerful mountain chains, with strong, thickened crust pushed deep into the hotter interior of the planet. Scientists have evidence showing that these early collisions stitched together cratons from what is now Canada, Greenland, Scandinavia, Southern Africa, and Western Australia into one of the most extensive landmasses early Earth had ever seen. Along the edges where these blocks collided, sutures developed. A suture is the zone where two continents have locked together, and it can be traced by highly deformed rocks, fragments of ancient ocean floor called ophiolites, and unique metamorphic minerals that only form under extreme pressures and temperatures. In many regions that once formed part of Kenorland, geologists map these sutures like fossilized front lines, using them as powerful clues to reconstruct the vanished supercontinent. But continental victory carries a hidden cost. As a supercontinent grows, it acts like a giant insulating blanket over the mantle. Heat builds beneath the thick crust, weakening it from below. Over tens of millions of years, this trapped heat can cause the lower crust to soften and stretch, while rising plumes of hotter mantle punch upwards. Tension cracks the continent, forming long linear rifts that split ancient mountain belts and tear through old sutures. With time, those rifts can open into new ocean basins. Volcanic margins develop, where lava floods out along the thinning edges of the continent, and mid-ocean ridges ignite in the center of the widening gap. Here, new oceanic crust forms and spreads, marking the birth of entirely new plates, while the pieces of the old supercontinent drift apart. This cycle of collision and rifting is one of the most violent, relentless engines on the planet, and it has played an important role in shaping Earth's surface and long-term habitability. Changing the positions of continents changes ocean currents, climate patterns, and the chemistry of the air and seas. When Kenorland finally begins to tear itself apart, those deep tectonic forces will not only redraw the map, they will send shockwaves into the atmosphere and climate system, setting the stage for the next great transformation, long before the first dinosaurs leave their bones in the rock. As Kenorland begins to split apart, the world does not simply rearrange its shorelines, it lurches toward one of the most extreme climate states in Earth's history. Many millions of years after the first rifts open, the planet enters a prolonged Paleoproterozoic ice age, with the Huronian glaciation standing out as one of the most severe and longest cold intervals ever recorded. For tens of millions of years, ice advances again and again, turning large parts of the planet into a frozen landscape. Scientists have evidence showing that this was not a local winter, but a global or near-global transformation. Glacial deposits of similar age appear in rocks spread across Canada, Scandinavia, India, and southern Africa. These distant regions were once fragments of Kenorland, carried far apart by later tectonic motions, yet they preserve matching signs of ancient ice. The pattern suggests that as the supercontinent broke, its scattered pieces all felt the grip of the same great freeze. In these rocks, the marks of vanished glaciers are still clear. Striated bedrock surfaces show long, straight scratches carved by stones frozen into the base of moving ice sheets. In marine sediments, outsized boulders known as dropstones sit in much finer mud, dropped from melting icebergs that carried them out to sea. Thick, chaotic layers of diamictite, full of mixed pebbles and larger clasts, record the debris left behind as glaciers advanced and then retreated. These features act almost like fossils of climate, giving strong evidence that powerful ice once reshaped the early Earth. What could drive such a dramatic chill on a planet warmed mainly by volcanic gases and a faint young sun? One leading hypothesis is that the breakup of Kenorland itself played an important role. As the supercontinent stretched and fragmented, it exposed vast new continental margins and broad, shallow seas. Fresh rock along these young coastlines weathered more rapidly, especially in warm, wet conditions, pulling carbon dioxide out of the atmosphere and locking it away in new minerals and sediments. With greenhouse gases reduced, the planet's natural insulating blanket weakened. The atmosphere trapped less heat, and global temperatures fell, allowing ice sheets to grow thicker and spread from high latitudes toward the equator. As the ice expanded, it created a world dominated by bright, reflective surfaces. This high albedo bounced more sunlight back into space, causing further cooling. Once this feedback loop took hold, the climate system could lock itself into a self-reinforcing freeze that was difficult to escape. This frozen aftermath of Kenorland shows how the destruction of a supercontinent can destabilize climate so severely that the entire planet edges toward being hostile to life at the surface. Could similar chains of events unfold again when later supercontinents form and break apart? The story of Kenorland is only the first chapter. In the deep future of Earth's past, other giant landmasses will rise and fall, and some of them will be linked to climate swings even more catastrophic than this early great ice world. As Kenorland's frozen world tightened its grip, another even more dangerous transformation was building in silence. It would not come from ice or fire, but from something far more familiar. It would come from oxygen in the air. Around 2.4 billion years ago, Earth experienced the Great Oxidation Event, one of the most transformative and deadly atmospheric shifts in its entire history. For millions of years before this turning point, tiny cyanobacteria in the oceans had already been hard at work, using sunlight to split water and release oxygen as a waste product. At first, this gas never reached the sky in large amounts. It was trapped and neutralized long before it could change the wider environment. In those early oceans, dissolved iron and volcanic gases acted like powerful chemical sponges. Free oxygen reacted quickly with iron to form rust minerals, and with gases like methane and hydrogen to form new compounds. Scientists have evidence showing that this process filled the seafloor with thick layers of banded iron formations, made of alternating dark iron-rich bands and lighter silica layers. These ancient rocks are like geological fossils of a time when almost every oxygen molecule was captured and locked away. The rise of large continents, such as Kenorland, changed that balance. As these strong blocks of crust grew higher and wider, rain, wind, and ice began to grind their surfaces down. Rivers carried the resulting sediments and nutrients into shallow coastal seas. This steady delivery of phosphorus and other key elements played an important role in fueling enormous blooms of photosynthetic microbes. In effect, the continents turned the oceans into vast biological reactors. With more nutrients came more cyanobacteria, and with more cyanobacteria came more oxygen. Eventually, biological productivity overwhelmed Earth's natural oxygen sinks. The iron in the oceans became saturated, volcanic gases could no longer consume all the new oxygen, and for the first time, free oxygen began to build up in the water, and then in the atmosphere. What had been a local waste product became a planetary weapon. For many of the early anaerobic organisms that had evolved in a low-oxygen world, this new gas was toxic. Oxygen attacked their delicate biochemistry the way strong acids attack metal. Entire microbial ecosystems that had thrived in oxygen-poor environments were pushed into crisis. How many ancient lineages vanished without leaving clear fossils behind? The rocks record this turning point. After the Great Oxidation Event, banded iron formations become rare, while red beds, sedimentary rocks stained with iron oxides, spread across the continents. These rusty layers are evidence showing that the atmosphere itself had become rich enough in oxygen to oxidize iron on land. In this way, continents acted as both creators and destroyers. Their weathering fed life, but their influence on global chemistry also helped unleash a catastrophe that reshaped the planet. Later supercontinents would repeat this pattern, weaponizing climate and chemistry in new ways. What other atmospheric revolutions waited as even larger landmasses gathered and broke apart many millions of years later? As the planet moved beyond those early atmospheric shocks, an even larger experiment in continental power began. Many millions of years after Kenorland, a new giant landmass gathered its fragments and rewired the deep Earth itself. This supercontinent is known as Columbia, or Nuna, and it may have been one of the most influential arrangements of rock and mantle in the entire Proterozoic. Columbia existed roughly between 1.8 and 1.5 billion years ago. In a global reconstruction, many of the same ancient cratons that once helped build Kenorland appear again, but in new positions and new combinations. Scientists have evidence showing that the strong cores of Laurentia, Baltica, Siberia, India, and several other blocks were stitched together into a single enormous landmass that stretched almost from pole to pole. On a time-lapse map, separate continents drift slowly across a dark ocean, then lock together into one continuous band of rock. How can such a lost continent be recognized when no familiar coastline survives? The answer lies in its scars. Around the world, mountain belts of similar age, from North America to Scandinavia to parts of Asia, record powerful collisions between these cratons. High-grade metamorphic rocks, baked and squeezed deep in former roots of those mountains, carry matching pressure and temperature histories. Large granite provinces, all crystallizing between about 1.9 and 1.6 billion years ago, line up along ancient sutures like healed fractures in a continental skeleton. These signatures do more than outline a vanished geography. They also hint at a change in how the planet's engine worked. Columbia's assembly marks a time when plate tectonics appears to have become more organized and long-lived, with large, stable plates dominating Earth's surface for hundreds of millions of years. Instead of short-lived fragments jostling chaotically, broad continental rafts slid over the mantle in a more coherent pattern. This stability allowed thick crust to grow, cool, and survive. A supercontinent of that size does not just sit passively on the mantle. It reshapes the flow beneath. When so much buoyant rock gathers in one place, it can act like a lid, trapping heat and altering convection cells below. Scientists have used models and deep seismic imaging as evidence showing that heat may have pooled beneath Columbia, reducing volcanism under its center, while enhancing powerful volcanic arcs around its margins. The edges of the continent likely glowed with long chains of volcanoes, where oceanic plates dove down and returned surface material to the deep interior. This new arrangement of rock, heat, and water played an important role in Earth's surface environment. By focusing most subduction and volcanic outgassing along its coasts, Columbia may have regulated how much carbon dioxide and other gases entered the atmosphere. At the same time, its vast interior highlands and long continental shelves provided enormous areas for weathering, washing nutrients into surrounding seas. Over millions of years, this balance between volcanic input and chemical drawdown could influence ocean chemistry, oxygen levels, and the slow expansion of early ecosystems. In this sense, Columbia was not just another continent. It was a profound reorganization of the crust and mantle. Its birth set patterns of plate behavior, climate feedbacks, and deep circulation that would echo through later supercontinents like Rodinia and, much later, Pangea. And when Columbia finally began to fracture, its breakup seeded new ocean basins and fresh continental outlines. Those changing shorelines would, in time, support more complex ecosystems, preparing the stage for future revolutions in life that still lay far ahead in Earth's story. Those new shorelines did not just reshape oceans. They helped usher in one of the strangest chapters in Earth's history. For nearly a billion years, from about 1.8 to 0.8 billion years ago, the planet entered what scientists call the boring billion, an interval that, at first glance, seems quiet compared with the violent impacts and global ice ages that came before and after. During this long stretch, supercontinents such as Columbia and its descendants were relatively stable. Instead of constant collisions and rapid breakups, the giant landmasses shifted slowly, locked together by strong belts of ancient crust. There is little evidence showing that the planet experienced the kind of planet-wide glaciations or massive volcanic outpourings that mark other eras. To many millions of years of slow change, the rocks record a kind of tectonic deep breath. Earth's atmosphere and oceans also appear to have settled into a quasi-steady state. Oxygen levels were higher than in the earliest Archean world, yet still far below modern values. The oceans likely held enough nutrients like phosphorus and iron to support life, but not in wild swings of feast and famine. Instead of extreme booms and crashes, productivity seems to have been steady, low, and persistent, spread across broad continental shelves and quiet inland seas. At first, this might sound like a geological lull, a time when little of importance happened. But stability can be one of the most powerful forces in evolution. Without constant catastrophe, cells had time to experiment. Over millions of years, slow genetic changes could accumulate, and fragile innovations did not face immediate destruction from sudden freezing or global lava floods. Within this calm, a profound biological revolution unfolded. Eukaryotes, cells with internal compartments, including a nucleus and energy-producing organelles, rose to prominence. Scientists have found microfossils from this interval that show larger, more complex cell shapes and thicker walls. clues that new ways of living were evolving. Continental margins, shallow seas, and lagoons around Colombia provided many different environments where these organisms could test new strategies for feeding, reproduction, and cooperation. The presence of large weathering continents played an important role in this story. As rain and wind broke down strong crystalline rocks, rivers carried a steady trickle of nutrients into the oceans. This gentle but continuous supply helped maintain a background level of photosynthetic life. It was not a raging bloom, but a long, dim glow, pumping oxygen into the air and building organic matter that altered the chemistry of seas and sediments. Tectonic calm, then, did not mean evolutionary stagnation. Beneath apparently uneventful skies, cell biology was being rewired, metabolic pathways were diversifying, and early ecosystems were becoming more intricate. The planet was loading the dice. When this long calm finally ended, and supercontinents broke apart while oxygen and nutrients surged, that hidden potential would combine with renewed upheaval to drive some of Earth's most extreme environmental crises, and eventually, explosions of complex life that would change the planet forever. As that long calm gave way to renewed motion in Earth's crust, a new experiment in continental power began. Many millions of years after Columbia fractured, the drifting fragments did not simply wander forever. They began to gather again, grinding together along ancient scars to form a landmass so vast that later supercontinents would stand in its shadow. Geologists call it Rodinia. Rodinia likely existed between about 1.1 billion and 750 million years ago in an alien world with no dinosaurs, no forests, and only simple life in the oceans. In this interval, strong plates of continental crust slowly converged, driven by deep currents in the mantle. The result was a single supercontinent that pulled together many of the blocks that are familiar on maps today. Laurentia, the ancient core of North America, locked against pieces that would become South America, Africa, Australia, and Antarctica. Reconstructing this lost giant is one of the most debated puzzles in geology. How did those pieces actually fit? Different research groups propose competing maps, rotating and sliding the cratons into various positions around Laurentia. Some models place what is now Australia snug against Western North America. Others push it toward the north. Scientists have built entire careers testing which version best matches the rocks. The core idea, however, is clear. Many of today's continents once formed a single continuous landmass. There is evidence showing that mountain belts of nearly identical age and character line up when those continents are reassembled. Sedimentary layers that formed along ancient coastlines show the same sequences of sandstones, shales, and carbonates, as if they were once part of one long shoreline instead of scattered around the globe. Paleomagnetic data adds another line of proof. Tiny magnetic minerals in ancient rocks recorded the direction of Earth's magnetic field when they formed. By measuring these signals, scientists have found that widely separated cratons shared similar latitudes during Rodinia time. This suggests that they were joined not thousands of kilometers apart. Some of the strongest evidence comes from the scars of collision themselves. In eastern and southern North America, the Grenville orogeny preserves the remains of a huge mountain chain that rose when continents smashed together between about 1.3 and 1.0 billion years ago. Similar aged orogenic belts appear in South America, Greenland, and perhaps Antarctica. Together they mark the welds that stitched Rodinia into place. This supercontinent was likely one of the most extensive ever assembled. By blocking and redirecting ocean currents, it played an important role in controlling global climate, nutrient delivery, and the chemistry of seawater. Its interior, far from the coasts, was probably dry, windy, and harsh. Around its long margins, broad shallow seas spread over the continental edges, collecting thick sediments and providing stable environments where early microscopic life could grow. But such concentration of land and heat also stored tension. Deep beneath Rodinia, mantle plumes and rising magma began to weaken the crust. The same forces that had built this powerful continent would eventually tear it apart, setting the stage for rifts, new oceans, and some of the most extreme ice ages the planet has ever seen. What happens when a supercontinent begins to crack? When that supercontinent began to crack, the result was not just new oceans and drifting fragments. Many millions of years later, the ghosts of Rodinia's broken pieces may have turned the entire planet into ice. This episode in Earth's history is known as Snowball Earth, one of the most extreme climate events ever proposed. Between about 720 and 635 million years ago, glaciers advanced again and again. Some climate models suggest that ice did not stop at the poles or mid-latitudes, but pushed all the way to the equator. In this vision, the blue planet became white. Oceans froze over, continents vanished beneath moving walls of ice, and sunlight bounced back into space from a bright, reflective shell. This idea is not just imagination. Scientists have found evidence showing that rocks formed by ancient glaciers, called tillites, occur in places that were once near the equator. Tiny magnetic minerals inside these rocks preserve the direction of Earth's magnetic field at the time they formed. By reading these paleomagnetic signatures, scientists have reconstructed past latitudes and shown that ice-carved deposits formed in what were then tropical regions. How could a warm equatorial belt turn into a frozen wasteland? Rodinia's breakup played an important role. As the supercontinent rifted apart, long new coastlines formed in low latitudes. Fragmented continental blocks drifted into the tropics, where intense sunlight drove strong evaporation, thick clouds, and heavy rainfall. This wet, energetic environment attacked fresh rock with powerful chemical weathering. During weathering, rainwater and weak acids react with silicate minerals, drawing carbon dioxide out of the atmosphere and locking it into carbonates that later become part of the crust. With so many young rifted margins in the tropics, this process accelerated. It was similar to what happened after the breakup of Kenorland, but on an even more extreme scale. As CO2 levels fell, the greenhouse blanket around Earth thinned. Global temperatures dropped, ice advanced, and bright new ice surfaces reflected even more sunlight, driving a runaway freeze. On a full snowball Earth, the oceans would have been capped by hundreds of meters of ice. Only thin films of liquid water might have persisted around seafloor hydrothermal vents, or in narrow belts of seasonal melt near the equator where cracks opened in the ice. Continents would have been buried beneath thick, grinding glaciers that scraped away soils and ground mountains into rock flour. Life faced a brutal test. Photosynthesis in surface oceans would have been throttled as light struggled to penetrate the ice. Food webs collapsed into tiny refuges. Dark vent communities on the seafloor, microbes clinging to pockets of brine inside the ice, and sparse algae in rare pools of open water. Could thin films of liquid really support a biosphere for millions of years? The same tectonic engine that tore Rodinia apart also kept volcanic arcs active. While the surface froze, volcanoes continued to pump CO2 into the atmosphere. With weathering nearly shut down under global ice, this greenhouse gas slowly accumulated. When concentrations finally grew high enough, the freeze ended in a violent thaw. Glaciers melted, oceans surged, and temperatures may have spiked to tropical conditions in only a few thousand years. Geologists see evidence of this dramatic shift in strange rock layers called cap carbonates. These are thick, often finely layered carbonate deposits that sit abruptly on top of glacial sediments. Their chemistry and textures suggest rapid precipitation from warm CO2-rich seas. They mark the moment when a planet locked in ice flipped back into a hothouse state. In this way, Rodinia's disintegration did more than rearrange landmasses. It nearly erased surface habitability, turning Earth into a survival puzzle for early life. Yet those survivors, hardened in hidden refuges, would inherit a transformed world. The end of Snowball Earth cleared the stage for new oceans, new coastlines, and soon after, one of the most dramatic evolutionary explosions the planet has ever seen. What forms of life were waiting to take advantage of this reborn environment? For millions of years, that reborn environment was still far in the future. During Snowball Earth, the planet stood on a knife edge, with ice stretching from pole to pole and only the faintest threads of habitability left. Yet life did not vanish. The very existence of complex fossils and rich chemical signatures in younger rocks is powerful evidence showing that ancient organisms somehow endured this frozen crisis. Scientists have pieced together several possible refuges where liquid water could survive beneath the global ice. Around submarine hydrothermal vents, hot fluids rose from the seafloor, creating dark oases in an almost completely sealed ocean. In cracks and thin patches of sea ice, narrow films of briny water may have remained unfrozen, allowing light to filter through. At the equator, shifting winds and currents could have opened polynyas, patches of open water surrounded by ice. Even beneath thick continental ice sheets, pressure and geothermal heat may have carved out hidden subglacial lakes, quiet basins of water completely cut off from the frozen surface. Inside these scattered sanctuaries, life adapted to conditions that would destroy most modern ecosystems. Microbial mats clung to rock around vents, using chemical energy instead of sunlight. Hardy algae and bacteria lived in the lower layers of sea ice, surviving on the weak light that passed through the frozen lid. Chemoautotrophs, which fed on dissolved minerals and gases, played an important role in keeping food chains alive when photosynthesis nearly collapsed. These communities were small and fragile, but they persisted for millions of years in a world that had almost stopped. Genetic studies add another layer of evidence showing that Snowball Earth did not reset life to zero. Molecular clocks in DNA suggest that many major eukaryote lineages, and even early branches leading toward animals, trace back to before or during these glaciations. This means the ancestors of later complex organisms did not appear in a warm, comfortable ocean. They were forged in a planet-wide icehouse, tested by relentless cold, low oxygen, and scarce nutrients. This was one of the most dangerous chapters in Earth's history. For incredibly long spans of time, the entire biosphere may have depended on a few isolated ecosystems. A vent field here, a crack in the ice there, a hidden lake beneath a crushing glacier. If any of those systems failed, would life on Earth have ended altogether? Under such pressure, survival demanded innovation. Extreme stress selected for organisms that could tolerate freezing temperatures, sudden changes in resources, and water starved of oxygen. Traits that allowed cells to resist damage, store energy, or enter dormant states became powerful advantages. When the ice finally retreated and volcanic carbon dioxide drove a greenhouse overshoot, torrential weather and rapid melting flooded the oceans with fresh nutrients from newly exposed rocks. That violent transition did more than thaw the seas. It reset circulation, mixed chemicals, and opened new coastlines and shallow shelves. In the wake of Snowball Earth, those once imprisoned lineages were released into a transformed world, rich with opportunity. The stage was set for one of the most dramatic bursts of diversification the planet has ever seen. But what forms would rise from the survivors of the deep freeze? In the wake of that frozen catastrophe, the world did not simply return to normal. It lurched into one of the most explosive chapters in the history of life. Around 541 million years ago, the Cambrian explosion began. A brief interval in deep time when strange new animals appeared in the fossils with astonishing speed. For millions of years before, life had been mostly simple. Then, suddenly, the record fills with bodies, shells, armor, and teeth. Scientists have long asked why this burst happened when it did. One idea links it directly to the breakup of Rodinia and the violent end of Snowball Earth. As that ancient supercontinent tore apart, the strong tectonic forces that had nearly frozen the oceans also reshaped the planet's surface. New continental margins formed around each drifting fragment, and wide epicontinental seas spread across low-lying crust. These shallow, sunlit waters became one of the most productive environments Earth had ever seen. Along those flooded shelves, rivers washed in nutrients from freshly exposed rock. The same intense weathering that drew down carbon dioxide during the Great Glaciations continued under post-snowball greenhouse conditions, but with a different effect. Instead of locking the planet in ice, it now delivered phosphorus, iron, and other key elements into the oceans. There is evidence showing that this chemical influx helped fuel dense blooms of algae and bacteria, pumping more organic matter into the food web than earlier ecosystems could support. At the same time, the atmosphere and oceans were changing in another crucial way. After the deep freeze, oxygen levels likely rose again, helped by vigorous circulation and the burial of organic carbon on those new continental margins. Higher oxygen meant that animals could grow larger, move faster, and power more complex bodies. Muscles, nerves, and active brains became possible on a new scale. Predators with grasping limbs and cutting mouthparts appeared, and prey responded with shells, spines, and thicker body walls. Teeth and armor began a biological arms race that played an important role in shaping Cambrian life. In places like the Burgess Shale of Canada, fossils preserve this transformation in remarkable detail. Many millions of years ago, that site lay along the edge of a continental fragment that had once been welded into Rodinia. Mudslides carried soft-bodied animals down a steep slope into deeper water, where fine sediment entombed them before scavengers or decay could destroy their remains. The result is one of the most famous windows into early complex ecosystems, built directly on the fractured rim of a vanished supercontinent. Taken together, these patterns suggest a powerful irony. The same shifting plates that assembled Rodinia, triggered global glaciations, and nearly erased complex life also built the stage for its greatest expansion. As future supercontinents like Pangea rise and break apart, similar cycles of collision, climate stress, and renewal will continue to create dangerous worlds that both threaten and empower life. What new winners and what new extinctions will those restless continents bring? The same tectonic forces that assembled Rodinia, triggered global glaciations, and nearly erased complex life did not rest for long. Many millions of years ago, as Rodinia broke apart, a new southern giant slowly took shape. This was Gondwana, one of the most powerful and enduring supercontinents in Earth's history. Gondwana was a vast puzzle made from pieces that are familiar today. It joined what are now South America, Africa, Antarctica, Australia, the Indian subcontinent, and Arabia into a single sweeping landmass wrapped around the southern half of the planet. For millions of years, these regions were not scattered across the globe. They were fused together, sharing the same mountain chains, coastlines, and ancient environments. Scientists have evidence showing that Gondwana began assembling in the late Neo-Proterozoic, more than 600 million years ago. As island arcs and older cratons collided, strong belts of deformed rocks and welded crust stitched the continent together. Once formed, Gondwana remained a dominant feature of the planet well into the Paleozoic era, persisting through the rise of early animals, the spread of land plants, and the appearance of the first land-walking vertebrates. How is such an ancient continent reconstructed when its original shorelines are gone? Scientists turn to matching clues scattered across modern continents. Identical fossil assemblages, such as the plant Glossopteris and the reptile Mesosaurus, are found in South America, Africa, India, and Antarctica, even though oceans separate them today. Thick layers of similar glacial deposits lie on these continents as well, showing that ice sheets once spread across a united southern land. Continuous mountain belts, like the ranges that connect Brazil to West Africa and Antarctica to Australia, line up almost perfectly when the continents are pushed back together on paleogeographic maps. World-building animations of Gondwana show a landmass stretching from polar to tropical latitudes. Its southern interior lay deep in the cold, while its northern margins reached warm, storm-rich seas. This range created deserts, coal-forming swamps, upland forests, and broad coastal shelves, all linked across a single supercontinent. Such diversity of climates and habitats played an important role in shaping Paleozoic ecosystems. Gondwana's position around the South Pole also controlled global ocean circulation and atmospheric patterns. During major glaciations, ice caps expanded over its highlands, sea level dropped, and cold, dense waters spilled into surrounding oceans. These shifts altered nutrient cycles, marine currents, and climate belts on a planetary scale. In many intervals, Gondwana was one of the most influential features on Earth's surface, rivaling the later Pangea in its reach and impact. Along its long, active margins, shallow seas and river plains became key evolutionary laboratories. Early land plant ecosystems spread across Gondwanan lowlands, stabilizing soils and pumping oxygen into the atmosphere. Offshore, complex marine communities with armored fish, reefs, and early predators flourished along its continental shelves. Without this southern giant, the environments that later allowed dinosaurs and other animals to dominate would have looked very different. But Gondwana's story is not one of quiet stability. Its slow drift toward northern continents will eventually drive new collisions, close ancient oceans, and help assemble Pangea. That coming impact will reshape climates again and set the stage for some of the most dangerous times in Earth's history. For many millions of years after Gondwana assembled, the continent did not only build mountains and close oceans, it also helped plunge the planet into one of the most persistent ice ages in Earth's history. This was the late Paleozoic Ice Age, a long cold interval stretching roughly from 360 to 260 million years ago, when glaciers advanced and retreated again and again across the southern supercontinent. Scientists have evidence showing that this glaciation was not a local event. Instead, it spread across what are now South America, Africa, India, Australia, and Antarctica. In all of these regions, geologists find the same strange signatures: scratched and polished bedrock where ice once dragged across the surface, thick layers of poorly sorted rock called tillites, and boulders dropped into ancient marine sediments by melting icebergs. These scattered deposits fit together like pieces of a puzzle when the continents are reassembled into Gondwana. The reason is simple but powerful. Gondwana was parked over the South Pole. With so much land sitting in high latitudes, winter snow did not fully melt in summer, and massive ice sheets could slowly grow to great thickness. Over millions of years, these frozen caps advanced toward lower latitudes, then retreated as climates shifted, leaving behind stacked layers of glacial sediments that still record each pulse of cold. Land plants played an important role in driving this icy climate. By the late Paleozoic, dense forests of ferns, seed ferns, and giant club mosses covered broad lowlands and swampy basins. Their roots broke down rock, increasing chemical weathering of silicate minerals. This process pulled carbon dioxide out of the atmosphere and locked it into new minerals and buried plant material. With less greenhouse gas to trap heat, global temperatures fell further, reinforcing the growth of ice on Gondwana. As glaciers waxed and waned, sea levels rose and fell by tens of meters. Shallow seas that once flooded continental margins dried out when water was locked in ice, then returned as the ice melted and water flowed back to the oceans. These repeated shifts reshaped coastal environments, drowning some habitats while exposing new ones, and they left clear sedimentary records on the edges of Gondwana's cratons. Yet this was not a world frozen everywhere. While high southern latitudes lay under powerful ice sheets, regions closer to the equator remained warm and often humid, with coal-forming forests and broad river plains. Strong climatic gradients crossed Gondwana, forcing plants and animals to adapt to very different conditions over relatively short distances. How did early forests respond when cold, dry winds pushed into once humid basins? These swings in temperature and moisture created intense evolutionary pressures. Amphibians, tied to water for reproduction, were limited by freezing seasons and shifting wetlands, while the first reptiles, with tougher skin and more resistant eggs, could push into drier and more seasonal interiors. In this way, the harsh Ice Age environment helped shape the rise of lineages that would later give rise to some of the most dominant land vertebrates, including future dinosaurs. Eventually, Gondwana began to drift northward and collide with other continents, helping to assemble Pangea. As the land moved away from the pole and mountain belts rose, the great ice sheets shrank. The ice retreated, but the price was paid in powerful mountain building, changing ocean circulation, and environmental upheaval that would set the stage for the next chapter in Earth's story. As the ice shrank from Gondwana's mountains, another kind of chill spread across the planet, a tightening ring of collisions that would end in a single giant landmass. For many millions of years, the southern Titan Gondwana and a chain of northern continents, including Laurussia, were drawn together by slow but relentless plate motions. Separate worlds of shoreline and shallow sea were on a collision course. By the late Paleozoic, this convergence had become one of the most dramatic tectonic episodes in Earth's history. Between what is now North America and Europe, the Variscan and Alleghanian orogenies slammed continental blocks together, welding them into the heart of Pangea. At the same time, farther to the northeast, the Uralian orogeny closed the gap between what would become Europe and Siberia. Each impact was like a slow-motion car crash measured in millions of years, but the damage was permanent. These collisions did not simply push land together, they crushed it. Thick piles of rock were squeezed, folded, and stacked to form enormous mountain ranges. The ancestral Appalachians, born from the Alleghanian collision, once rose to heights that may have rivaled the modern Himalayas. To the east, the Urals stretched from the tropics toward the polar regions as a long, strong scar in the crust, a physical record of continents that had once been oceans apart. Scientists have traced these ancient belts using fossils, rock types, and magnetic signatures that still point back to the time of impact. Under the surface, the violence was even greater. As plates jammed together, the crust crumpled and thickened, and the lithosphere sank deeper into the mantle. Subduction zones shifted or shut down, and entire ocean basins were rerouted or destroyed. There is evidence showing that these were among the most powerful continent-building events the planet has ever seen, reshaping not only the land, but the pathways of deep ocean currents. As Pangea neared completion, the world's geography changed in a fundamental way. Coastlines that had once surrounded many smaller continents vanished as the land fused into a single, sprawling interior. Shallow epicontinental seas drained away, replaced by vast continental plains far from any ocean. What happens to climate when the sea is pushed to the edges of a world? With fewer coastlines, ocean circulation patterns reorganized, and seasonal contrasts sharpened. Monsoon systems strengthened along the margins of Pangea, while the deep interior became dry and highly seasonal. Large desert belts spread across the central supercontinent, while rainforests and swampy lowlands were squeezed into narrower coastal zones and rift valleys. This new environment played an important role in deciding where life could thrive and where it struggled. Pangea was one of the most extreme continental configurations possible, a true monster continent with the power to reshape climate, ecosystems, and evolution on a global scale. Long before it became the stage for giant dinosaurs with strong legs and deadly teeth, its assembly helped trigger some of the most devastating environmental crises in Earth's history. The final welding of this supercontinent would coincide with mass extinctions so severe that entire branches of life vanished, clearing the way for new worlds to rise in its shadow. As supercontinents rise and fall, they do more than reshape coastlines. They turn the entire planet into a dangerous machine. Scientists have strong evidence showing that many of the most severe mass extinctions cluster around moments when the continents lock together or tear apart, as if life itself is caught in the gears of moving rock. When continents assemble into a single giant landmass, the interior of that world becomes harsh and unforgiving. Moisture from the oceans struggles to reach the center, creating vast arid regions with powerful seasonal winds and extreme temperature swings between day and night. Instead of long, gentle coasts, there are dry basins and deserts stretching for thousands of kilometers. For plants and animals living many millions of years ago, these conditions could turn once stable habitats into lethal traps. The oceans suffer as well. During supercontinent assembly, shallow continental seas are often squeezed out as blocks of crust collide and coastlines are welded together. These flooded shelves are one of the most productive environments on Earth, home to reefs, dense communities of shellfish, and countless small creatures that form the base of marine food webs. When those broad sunlit platforms vanish, entire ecosystems can be wiped out, leaving only deeper, colder waters where fewer species can survive. The breakup of a supercontinent brings a different kind of danger. As the crust stretches and rifts open, huge volumes of magma can rise from deep within the mantle, forming large igneous provinces. These volcanic outbursts do not look like single dramatic eruptions. Instead, for hundreds of thousands, or even millions of years, lava floods across the land and seafloor, while gases pour into the atmosphere. Carbon dioxide, methane, and sulfur compounds build up, driving rapid warming, ocean acidification, and episodes of toxic rain. Could any complex biosphere remain unchanged under such stress? Across Earth history, these tectonic pulses align with biological crises again and again. The assembly of Rodinia appears to have played an important role in long global glaciations and major turnovers in early marine life. Later, as Gondwana shifted and collided with other blocks, changing sea levels and climates altered ecosystems on a planetary scale. Even older supercontinents, such as Kenorland, show hints of similar patterns in the rocks, with ancient fossils and isotopes recording sudden environmental shocks. These records reveal that continents are not passive backdrops for evolution. Their movements are one of the most powerful drivers of global environmental change, capable of stripping away shallow seas, baking interiors, and then drowning the air in volcanic gases. Each cycle clears ecological space, destroying dominant groups and opening paths for new lineages to rise. As Pangea finishes forming and then begins to crack apart, these forces reach a terrifying peak. Ahead lies the Permian-Triassic crisis, the deadliest extinction in Earth's history, where nearly all complex life is pushed to the edge. Out of that devastated world, in the shattered landscapes of a broken supercontinent, the first true dinosaurs will step forward. By the time that broken world appears at the end of the Permian, the stage has already been set by far older continental dramas. Long before Pangea, other giant landmasses had come and gone. Valbara, Ur, Kenorland, Columbia, Rodinia, and Gondwana. Each of these ancient supercontinents rose from scattered crust, fused into powerful blocks of land, and then tore apart again until almost no surface trace remained. Every time the continents collided, mountains were raised, oceans closed, and volcanic chains poured gases into the air. Every time they split, new ocean basins opened and fresh seafloor reacted with the water and atmosphere. These cycles did not just reshape coastlines, they rewired climate, ocean chemistry, and oxygen levels. Scientists have found evidence showing that each round of assembly and breakup pushed life to its limits, then rewarded the survivors with new habitats and new evolutionary pathways. Early continents also changed the planet from within. As thick, buoyant crust stabilized, it insulated Earth's interior and created permanent land above sea level. Rivers carried nutrients from those first granitic highlands into the oceans, feeding microbial mats and early algae. Under brighter sunlight and in shallow coastal seas, photosynthesis intensified. Over hundreds of millions of years, this slow, relentless process helped oxygenate the atmosphere, turning a hostile world into one where active, large-bodied animals could eventually breathe deeply and move with strength. This long preparation was not gentle. During the time of Rodinia, global glaciations turned Earth into something close to a snowball planet. Ice reached near the equator, and the oceans may have been sealed under frozen lids. Yet life endured in cracks, vents, and thin belts of open water. That survival hardened the biosphere. When the ice finally retreated and Rodinia broke apart, oxygen levels rose again and the Cambrian explosion followed, filling the seas with one of the most dramatic bursts of new body plans in the history of fossils. From those experiments came vertebrates with internal skeletons, jaws, and eventually lungs. Fins stiffened into limbs. Simple gill-breathing swimmers gave rise to creatures that could push onto land, inhale air, and support their weight with strong bones. Terrestrial ecosystems began as low spore-covered wetlands, but they would not stay that way for long. Gondwana, the great southern supercontinent, became the cradle for vast forests, coal swamps, and early reptile lineages. Its position near the poles at times and closer to the equator at others drove powerful monsoons and repeated glaciations. These shifting climates played an important role in testing plants and animals. Only those able to handle drought, cold, and heat could thrive in its broad interior. By the time Pangea finally formed, Earth's biosphere had been forged in billions of years of tectonic chaos and climate catastrophe. Dinosaurs would inherit a world already stocked with forests, complex food webs, and animals capable of rapid growth and high activity. In that sense, they were not the beginning, but the latest champions in a long continental war. They became one of the most dominant and dangerous groups in Earth's history because the planet itself had trained life to be tough. To see why those predators and giants reached such power, the rise and fall of Pangea must be watched in detail, because within that supercontinent's story, the age of the dinosaurs truly begins. Long before Pangea gathered the dinosaurs on one vast stage, another giant continent had already ruled the planet's surface. It rose from the wreckage of even older lands, locked itself together, and then helped drive Earth into one of the most brutal deep freezes in its history. That ancient supercontinent is called Rodinia. Rodinia formed roughly 1.1 to 0.9 billion years ago, many millions of years before the first dinosaur left a footprint in the mud. During this time, fragments of far older continents, including pieces that once belonged to Kenorland and other vanished lands, were pushed together by powerful plate forces. Cratons that had drifted separately for hundreds of millions of years collided, their strong ancient rocks welding into a single enormous landmass. The result was one of the most stable and long-lived supercontinents ever assembled. Reconstructing this lost world is not simple. No coastlines survive, and its mountains have been worn down almost to their roots. Instead, scientists have turned to the rocks themselves, reading them like broken bones from a shattered skeleton. Matching belts of deformed rock in North America, Australia, Antarctica, and Asia line up like torn scars that once formed continuous mountain chains. These scars are powerful evidence showing that distant regions were once pressed tightly together along the same collision zones. Paleomagnetic clues add another layer to the puzzle. When lava cooled on Rodinia's surface, tiny magnetic minerals inside aligned with Earth's magnetic field, freezing in a record of latitude and direction. Scientists have measured these signals in ancient rocks and found patterns that repeat across continents, indicating that they once shared the same orientation in space. Ages of zircon crystals and other minerals from these rocks also match, giving evidence showing that the crust formed and deformed at the same times. Even so, the exact layout of Rodinia is still debated, with competing models rotating and sliding continents into different positions. Despite these uncertainties, one picture is widely accepted. Rodinia was a massive, almost continuous landmass straddling the equator, surrounded by a global ocean. Its coasts felt warm tropical rains, but its huge interior lay far from the sea. There, under clear skies and thin, dry air, deserts stretched for thousands of kilometers. Summers were intensely hot, winters surprisingly cold, and strong seasonal contrasts shaped the environment and the pace of erosion. In such a world, rivers carried limited nutrients to the ocean, and weathering of rock may have slowed. That quiet stability played an important role in what came next. With most land locked into one block, volcanic gases, erosion rates, and ocean circulation shifted in subtle but dangerous ways. Over time, carbon dioxide levels in the atmosphere may have dropped. The planet edged toward a tipping point. Rodinia's long night was coming, and the stage was being set for something extraordinary. Ice that would reach from the poles toward the equator, and a near-frozen ocean in the Snowball Earth episodes that followed. As Rodinia's long night approached, the land itself began to whisper clues. The supercontinent is gone, its coasts erased, but its scars remain. To rebuild it, scientists turned to those scars like detectives at an ancient crime scene. One of the most important clues comes from mountain belts that no longer stand as mountains. Along the eastern edge of North America, rocks of the Grenville orogeny record a powerful collision that took place more than 1 billion years ago. Their minerals were squeezed, melted, and recrystallized under extreme pressure. Matching belts with the same age and deformation style appear in Brazil, in West Africa, in Antarctica, and in India. Scientists have traced these ghost ranges across the globe, using their ages and structures as evidence, showing that fragments of crust now separated by oceans once formed a single continuous chain along Rodinia's edge, but mountains alone cannot reveal where that edge sat on the planet. For that, scientists rely on paleomagnetism, the faint magnetic memory locked inside ancient rocks. When lava cooled or sediments hardened many millions of years ago, tiny iron-bearing minerals inside lined up with Earth's magnetic field like microscopic compass needles. By measuring the direction and inclination of that frozen magnetism, researchers can tell the latitude where those rocks first formed and whether they pointed toward or away from the ancient poles. In this way, a billion-year-old basalt in Canada or a sandstone in South China becomes a time capsule, recording how Rodinia was tilted, rotated, and stretched across the globe. A different line of evidence comes from ancient volcanism. During the birth and breakup of supercontinents, huge pulses of magma rose from deep within the mantle, creating large igneous provinces that covered vast regions in thick layers of basalt. Scientists have mapped out these volcanic blankets by their age and by their distinctive chemical signatures. When rocks in Laurentia, Australia, and Antarctica all show the same pulse of rift-related volcanics at nearly identical times, it suggests that those areas were once joined, tearing apart along the same growing rifts as Rodinia began to fragment. Yet even with these strong clues, Rodinia remains one of the most debated jigsaw puzzles in Earth history. Did Australia once nestle against the western margins of North America, sharing mountain belts and rift scars? Or did it sit closer to Antarctica and India instead? Different reconstructions use the same sets of rocks and magnetic data, but slide the cratons into different positions, like shifting the same bones into alternate skeletons. The evidence is powerful, but not complete. This uncertainty keeps Rodinia alive as a scientific mystery. How can a continent that scientists can almost outline still hide its most dangerous secrets about climate, life, and the deep engine of plate tectonics? The next clues lie even deeper in the chemistry of ancient oceans and the first fragile traces of life that clung to Rodinia's shifting shores. Those chemical traces lead into one of the most misunderstood chapters in Earth's history. For almost a billion years, from about 1.8 to 0.8 billion years ago, the planet was once described as locked in a long quiet pause that scientists called the boring billion. During this interval, the supercontinent Rodinia gathered most of Earth's land into a single sprawling mass. The climate seemed mild, with no clear signs of global ice ages. Oxygen in the atmosphere appeared low and steady. Tectonic plates appeared to move slowly. For many years, this period was treated as a flat line between earlier violent change and the later explosions of complex life and dramatic climate swings. It looked calm, almost empty. But the rocks tell a different story. In the last few decades, scientists have uncovered evidence showing that this boring world was quietly transforming. Tiny changes in the chemistry of ancient shales and carbonates record a slow, stepwise rise in oxygen in the oceans and atmosphere. Iron formations thin out, while certain sulfur and molybdenum signals hint that deep waters were beginning to hold more oxygen in some regions. These shifts were small compared to later events, yet they played an important role in preparing the planet for future biological leaps. At the same time, nutrient cycles were being reshaped. With most land welded into Rodinia, vast interiors lay far from the sea. The continent's surface was thought to be low and broad, with gentle hills rather than sharp mountain chains. Such low-relief landscapes erode slowly. Rivers carry less phosphorus and other key nutrients to the ocean. In this environment, life in shallow seas may have remained simple for many millions of years, dominated by microbial mats and plankton that rarely faced sudden surges of food. This slow erosion had powerful consequences. Limited nutrient delivery likely kept primary productivity modest, which in turn restricted how fast oxygen could build up and how complex ecosystems could become. There were no forests, no animals, no dinosaurs, only microbial communities tracing out thin films along Rodinia's coasts. The world looked stable, but that stability masked a delicate balance between the continents, the oceans, and the air. Beneath Rodinia, however, the deep engine of plate tectonics was still working. Heat from Earth's interior gathered under the giant continent. Subduction zones chewed at its edges. Quiet rearrangements shifted plates by a few centimeters each year. Scientists have found subtle magnetic signatures and age patterns in zircon crystals that suggest Rodinia was never truly static. Instead, it was slowly storing mechanical and chemical tension. In this way, the boring billion becomes one of the most important, hidden buildup phases in Earth history. The planet's atmosphere crept toward higher oxygen, its nutrient cycles inched toward instability, and its strong, fused crust accumulated stress. When Rodinia finally began to crack, all of that stored pressure would be released. What happens when a seemingly calm world suddenly tips into chaos? When that calm world finally tipped, it did so along lines of fire. Around 800 to 750 million years ago, Rodinia began to rip apart. Great rift valleys opened through the supercontinent's interior. Lava flooded across the surface, and new ocean basins started to form where solid crust had once been fused together. What looked like slow tectonic drift from space was, on the ground, a drawn-out catastrophe for the planet's climate. As Rodinia stretched and thinned, blocks of crust were uplifted, fractured, and exposed. Fresh, sharp-edged rock surfaces met rain, wind, and chemically active seawater for the first time. This was not gentle erosion. It was intense chemical weathering on a continental scale, grinding and dissolving minerals that had been locked away deep in the crust for many millions of years. Those reactions quietly pulled carbon dioxide out of the air and delivered it into the oceans as dissolved carbon. This process is part of Earth's carbon dioxide thermostat. When new mountains rise or rifts expose fresh rock, rainwater reacts with minerals, forming bicarbonate ions that wash into the sea and later become carbonate rocks. Over long timescales, this draws down atmospheric CO2. With less CO2, the greenhouse effect weakens, and the planet's surface loses more heat to space. If the drawdown is strong and fast enough, global temperatures can plunge. Could drifting continents alone really turn Earth into ice? Scientists have gathered evidence showing that the answer is almost certainly yes. As Rodinia fragmented, continents shifted toward the tropics, where warm, wet conditions made weathering even more powerful. Large volcanic provinces first released CO2, but the freshly broken surfaces they left behind helped remove it again even faster. In this unstable environment, the balance between volcanic input and chemical removal of carbon dioxide tipped. The result was one of the most extreme climate swings in Earth history. During the Cryogenian period, starting about 720 million years ago, massive glaciations gripped the planet. The Sturtian glaciation, in particular, may have locked ice across nearly every ocean. Glacial deposits from this time are found on rocks that formed near the ancient equator, an environment that should have been warm. Yet the rocks tell a different story. They show that glaciers reached sea level in tropical regions, suggesting a true or near-true snowball Earth. On multiple continents, scientists have found physical traces of this frozen catastrophe. There are dropstones, large pebbles and boulders carried by icebergs and released into fine sea mud as the ice melted. There are glacial striations, long parallel scratches carved into hard bedrock by moving ice. And above many of these icy layers lie strange cap carbonates, thick sheets of carbonate rock that formed rapidly once the climate flipped back to extreme warmth. Together, this evidence showing that ice advanced to low latitudes and then retreated suddenly ties the Cryogenian ice ages directly to the tectonic chaos unleashed by Rodinia's breakup. In tearing itself apart, a supercontinent had nearly frozen the entire planet. How did life endure under a global shell of ice? And what happened when that shell finally cracked? Under a planet-wide shell of ice, Earth became one of the most hostile environments life has ever faced. For millions of years, frozen oceans stretched from pole to pole, and brilliant white ice and snow bounced much of the sun's energy back into space. Global temperatures plunged, the air grew thin and dry, and the normal exchange of heat and moisture that powered ancient climates nearly stopped. In this snowball Earth state, the surface ocean was locked beneath thick, grinding ice. Powerful glaciers flowed off the continents, scouring rocks and burying coastlines. The reflective surface of the ice amplified the cold, creating a feedback loop that kept the planet frozen. For complex organisms, this would have been a death sentence. Yet, microscopic life had already spread through the seas many millions of years ago, and it did not disappear. Scientists have proposed several refuges where liquid water and energy could still exist under these extreme conditions. Around the equator, winds and currents may have kept the sea ice slightly thinner, allowing dim light to filter through. In these marginal zones, photosynthetic microbes and simple algae could cling to life, forming thin layers just beneath the ice. Even a few meters of liquid water would have played an important role in keeping these fragile ecosystems alive. Far from the light, deep-sea hydrothermal vents likely continued to roar along mid-ocean ridges. Here, superheated, mineral-rich fluids rose from the crust into the dark ocean, creating steep chemical and temperature gradients. Microbes that fed on chemical energy rather than sunlight could thrive in these oases, completely insulated from the frozen surface. Evidence showing that vent communities are independent of sunlight in the modern ocean supports the idea that similar systems sustained life during snowball Earth. On and around the continents, volcanic islands and rift zones may have punched through the ice, forming local regions of open or thin water. Subglacial lakes, like those found beneath Antarctica today, and salty brine channels within the ice itself, could have sheltered dense microbial mats. Scientists have discovered hardy organisms in present-day polar brines and under thick ice sheets, evidence showing that such habitats are realistic analogs for cryogenian refugees. In these scattered pockets, early eukaryotes, simple algae, and layered microbial communities likely persisted. They would have grown slowly, endured long dark periods, and survived repeated advances and retreats of ice. Many lineages must have vanished, but a critical thread of continuity remained. This near-extinction event, driven in part by the rearrangement of continents that altered ocean circulation and atmospheric gases, acted like a planetary filter. Which traits allowed survival under such relentless cold? Resistance to freezing, flexible metabolisms, and the ability to form resting stages may have been decisive. When the ice finally began to crack and retreat, the survivors were not the same as those that had entered the freeze. The world that emerged would be primed for new evolutionary experiments, leading eventually to far more complex and ultimately more dangerous forms of life. The survivors of the Great Freeze emerged into a world on the edge of another catastrophe. For millions of years, Earth had been locked in snowball conditions, but deep beneath the ice, the planet's interior never stopped moving. While the surface lay silent, volcanoes kept erupting along rift zones and subduction margins, pouring gases into an atmosphere that could no longer behave in a normal way. Under ordinary conditions, carbon dioxide from volcanoes is balanced by weathering. Rainwater reacts with rocks on the continents, carrying dissolved carbon into the oceans, where it eventually becomes limestone and other carbonate rocks. During Snowball Earth, those strong chemical breaks failed. With continents buried under thick ice, there was almost no liquid water to wash over bare rock, so the usual weathering reactions nearly stopped. Volcanoes still pumped out CO2, but almost nothing removed it. Over immense spans of time, this imbalance created one of the most extreme greenhouse buildups in the planet's history. Scientists have modeled CO2 levels climbing to tens or even hundreds of times modern values. Sunlight that once bounced harmlessly off bright ice began to be trapped by this dense blanket of greenhouse gas. At first, the change would have been slow and almost invisible. Then the system reached a tipping point. Once enough CO2 had accumulated, the greenhouse effect finally overpowered the reflectivity of the global ice. Slight warming darkened the surface, as patches of open water and exposed rock absorbed more sunlight. That extra heat melted more ice, which exposed even darker surfaces, which captured still more energy. The feedback accelerated. Instead of a gentle spring, Earth experienced a violent planetary thaw. Geological outcrops on several continents preserve evidence showing that this transition was sudden and dramatic. Directly above glacial deposits, thick, unusual carbonate layers appear, known as cap carbonates. These rocks often contain strange wave-like structures and crystal forms that point to warm, chemically unstable oceans saturated with dissolved carbon. In many regions, the shift from gritty glacial sediments to smooth cap carbonates happens over just a few meters of rock, recording a rapid swing from deep freeze to hothouse conditions. These cap carbonates are one of the most striking signatures of the snowball aftermath. Their global distribution suggests that the oceans became a powerful sink for the volcanic CO2 that had built up in the air. As the ice vanished, intense rainfall, rapid weathering, and torrential runoff flushed ions into the sea, where they combined with dissolved carbon to precipitate vast blankets of carbonate mud. The end of the freeze reset not only climate, but also ocean chemistry. Behind this chain of events stood Rodinia. Its assembly had played an important role in driving the planet into ice, but its breakup fueled the escape. Rifting continents opened new volcanic belts and released enormous amounts of gas from Earth's interior. The same tectonic forces that froze the surface also loaded the atmosphere with the greenhouse fuel that melted it again. When the ice finally retreated and the cap carbonates settled, the planet had been rebooted. What new forms of life would this unstable, post-Rodinia world allow to evolve? When the ice finally loosened its grip, the world that emerged was not the same planet that had gone in. The end of Snowball Earth did not simply melt glaciers. It unlocked a new kind of power in the oceans and the air. For many millions of years before, Earth's atmosphere had been relatively poor in free oxygen. Simple microbes survived, but energy was limited and food chains were short. After the great glaciations tied to Rodinia's breakup, there is evidence showing that oxygen levels in both the oceans and the sky rose sharply. Iron formations that had once soaked up oxygen like a sponge began to fade, and red, rust-colored sediments spread on land. This shift created richer, more energetic environments where cells could burn fuel more efficiently and build larger, more complex bodies. The changing continents themselves played an important role in this transformation. As Rodinia tore apart, long new coastlines and shallow continental shelves appeared. Fresh rock was lifted, fractured, and then attacked by wind, rain, and powerful rivers. Intense chemical weathering washed pulses of nutrients, such as phosphorus and iron, into the seas. In many regions, black shales and organic-rich layers record sudden blooms of microscopic algae. Scientists have linked these nutrient surges to thicker, more intricate food webs, where sunlight captured at the surface could be passed upward through many different levels of life. In this new world of rising oxygen and restless shorelines, the nature of life itself began to change. During the Ediacaran period, strange multicellular organisms spread across the seafloor. Some looked like fronds pressed flat into the sediment, others like quilted discs or ribbed ovals with no obvious heads, teeth, or bones. Simple animals with burrows and soft bodies started to disturb the seafloor, leaving faint traces instead of hard fossils. These were not dinosaurs or even close relatives, but they were one of the most important early experiments in building large, organized bodies from many cooperating cells. Environmental stress, followed by sudden opportunity, seems to have opened new evolutionary pathways. The freeze-thaw cycles, shifting coastlines, and nutrient pulses that followed Rodinia's collapse repeatedly pushed life to the edge, then rewarded any lineage that could adapt to higher oxygen and more complex food webs. In effect, the planet had moved to a higher evolutionary setting, like a new level in a long game where the rules of survival had quietly changed. This pattern would not be unique to Rodinia. Later supercontinents, from Gondwana to Pangea, would also assemble, break apart, and rearrange oceans and climates. Each cycle rewrote habitats, reset ecosystems, and prepared the stage on which later giants, including the most dangerous dinosaurs with their strong jaws and slicing teeth, would eventually appear. What happened after Rodinia was only the first rehearsal for the continental dramas still to come. Rodinia was not Earth's first experiment with a giant landmass. For millions of years before it formed, even older supercontinents had already risen, collided, and vanished, leaving behind only scattered clues in ancient rocks. To follow their trail, scientists must look far beyond the age of dinosaurs and into a deeper, stranger world. One of the most important of these earlier giants is known as Columbia, also called Nuna. This supercontinent likely assembled between about 1.9 and 1.6 billion years ago, when many of the planet's oldest cratons were welded together into a single, powerful block of land. The pieces that would later become North America, Baltica, India, and other regions were not yet separate continents. Instead, they formed a continuous chain of crust, wrapped around the globe in patterns that can only be reconstructed from the faintest hints. What kind of hints can survive for almost 2 billion years? The main evidence comes from long linear mountain belts that match across oceans, from similar ages of igneous rocks, and from shared episodes of intense metamorphism. Rocks in Laurentia, the ancient core of North America, preserve strong signs of collision that line up in age and style with rocks in Baltica and parts of India. Scientists have found evidence showing that these distant regions experienced the same bursts of heating, burial, and uplift at the same times. The simplest explanation is that they once lay side by side along Columbia's active margins. Like later supercontinents, Columbia did not last. Over hundreds of millions of years, rifts opened, oceans invaded, and the great landmass fragmented. Yet its breakup played an important role in shaping the crust that Rodinia would later inherit. Repeated cycles of collision and separation thickened the continents, recycled older rocks, and changed the chemistry of the surface in ways that would eventually influence the oceans, the atmosphere, and the environments where life slowly diversified. Even Columbia, however, may not mark the true beginning of Earth's continental story. Some researchers propose still earlier supercontinents or large protocontinents with names like and Antarctica. These possible landmasses reach back more than 2.5 billion years into a time when the planet's heat flow was higher and plate motions may have been faster and more violent. Their outlines are highly uncertain, built from fragmentary cratons, isolated zircons, and paleomagnetic signals that are difficult to interpret. Are these real supercontinents or just temporary clusters of early crust? Each candidate tells the same deeper story. Again and again, continents gathered into vast assemblies, then tore apart, their strong interiors surviving while their edges were ground down and pushed into the mantle. With every cycle, the crust became thicker, more stable, and more chemically complex. Those long hidden preparations set the stage for later worlds, including the rich, dinosaur-filled environments that would only appear after many more supercontinents had come and gone. With those ancient building blocks in place, Earth's surface began to move to a deeper rhythm. For hundreds of millions of years at a time, scattered fragments of crust drifted apart, only to be drawn back together into single, giant landmasses. This repeating pattern is known as the supercontinent cycle, and it behaves like a slow, powerful heartbeat that has pulsed through more than 500 million years of planetary history. In each cycle, continents start widely separated, surrounded by broad oceans. Driven by plate tectonics, they slowly migrate, collide, and weld into one enormous supercontinent. After that, the same forces that built this giant landmass eventually tear it apart again, opening new oceans between the fragments. Scientists have measured the timing of these events and found that this full sequence of assembly and breakup tends to repeat every 400 to 600 million years. It is not a perfect clock, but it is one of the most reliable long-term patterns in Earth's story. Deep beneath the crust, mantle convection provides the main engine for this motion. Hot rock rises from deeper layers, spreads beneath the plates, then cools and sinks back down, dragging the surface pieces with it. Where old oceanic plates plunge into the mantle, slab pull exerts a strong downward tug, pulling attached continents toward convergent margins and setting up collisions. At the same time, when a supercontinent forms, its huge area insulates the mantle beneath it, trapping heat. Over many millions of years, that trapped heat can weaken the thick crust and help trigger rifts that split the land apart. How is this invisible heartbeat tracked? Instead of dinosaur bones, scientists rely on ancient mountain belts, rift zones, and enormous volcanic scars. There is evidence showing that the ages of major collision-built ranges line up in clusters, marking times when many continents crashed together. In other periods, wide rift valleys and flood basalts of large igneous provinces appear across the globe, recording times of breakup. When these patterns are compared, repeated peaks emerge that match supercontinents such as Columbia, Rodinia, Gondwana, and finally Pangea. These reconstructions are supported by paleomagnetic signatures frozen into rocks, by matching mineral belts on continents now oceans apart, and by radiometric dates that tie distant regions to the same events. Together, they show that the supercontinent cycle has played an important role in shaping not only the map, but also the planet's entire environment. Each assembly raised huge mountain chains, altered ocean currents, and changed how carbon and nutrients moved through air and sea. As continents cluster near the poles or spread across the tropics, climate can swing between hothouse conditions and nearly global ice ages. Massive volcanic outbursts during breakup episodes can flood the atmosphere with greenhouse gases or toxic aerosols, driving extinctions. In turn, these environmental shocks guide evolutionary booms and crashes, clearing ecological space and then filling it again. Could the rise of complex life and later the age of dinosaurs have depended on the timing of these deep pulses? The next sections follow how one early supercontinent cycle set the stage for some of the most extreme events Earth would ever face. Those deep pulses in Earth's interior did not just move plates slowly, they tore Rodinia apart. Many millions of years ago, long fractures opened across the supercontinent's interior, turning once continuous crust into a maze of sinking valleys and rising shoulders. In some regions, these rift zones stretched for thousands of kilometers, like invisible knives cutting through ancient granite and gneiss. As the crust thinned, it began to sag. Great linear basins formed, flanked by strong, uplifted ridges. Rivers poured into these new lowlands, carrying sediments from the eroding highlands. But the real transformation came from below. Mantle rock rose to fill the space, partially melted, and fed chains of volcanoes along the rifts. Over time, these valleys widened into the first outlines of new ocean basins that would become the distant ancestors of later seas. In several phases, the rifting did not just build volcanoes, it unleashed flood basalts. Scientists have evidence showing that vast volumes of lava spilled out through long fissures, rather than single peaks, covering regions the size of modern countries. Layer upon layer of basalt flooded across Rodinia's broken surface, in some places piling up several kilometers thick. These igneous plateaus, preserved today in fragments scattered on different continents, are one of the most important fingerprints of Rodinia's final breakup. In what is now South China, Australia, Laurentia, and other cratons, geologists map thick volcanic sequences of similar age and chemistry. Matching magnetic directions locked inside these rocks, scientists have reconstructed how those pieces once fit together along ancient rift margins. The same strong basalt layers that once formed a continuous volcanic province are now separated by entire oceans. Silent evidence that the supercontinent's crust was pulled apart and rearranged. As the rifts deepened and newborn oceans opened, the edges of the drifting fragments changed character. Stretched continental crust became thinner and more flexible, then slowly subsided under its own weight. Along these new passive margins, the sea advanced. Shallow epicontinental seas spread inward, turning former continental interiors into broad, sunlit shelves. These drowned edges became vast sediment traps. Rivers delivered mud, sand, and dissolved nutrients from the eroding volcanic highlands, feeding plankton blooms in the shallow water. Carbonate platforms and tidal flats grew along gentle slopes, while deeper parts of the shelves collected fine, dark muds. This quiet but persistent burial of sediments played an important role in reshaping the global environment, drawing down carbon and altering ocean chemistry. For early complex life, these changes were an opportunity. Expanding continental shelves created new gradients of depth, light, and nutrients, offering a mosaic of habitats rather than a single steep continental slope. Scientists have found fossils and chemical signals in late Neoproterozoic rocks, suggesting that eukaryotes and early animals diversified in these settings. Could the violent death of Rodinia, with its rifts, lava floods, and drowned margins, have prepared the stage for later biological revolutions, including the rise of the dinosaurs many millions of years after? The next chapter follows how the oceans and climate responded as the next supercontinents assembled and broke apart again. As Rodinia's fragments drifted apart and the climate lurched between extremes, a new continental giant began to take shape in the south. This was Gondwana, a vast supercontinent that would become one of the most important landmasses in Earth's history. Long before Pangea, it formed the hidden skeleton beneath the future world of the dinosaurs. Gondwana did not appear in a single moment. Between roughly 650 and 500 million years ago, older cratons and microcontinents slowly collided, welded, and thickened into a single southern giant. The pieces are familiar names today: the cores of South America, Africa, Antarctica, Australia, the Indian subcontinent, and Arabia. Many millions of years later, these regions would sit far apart, but in this earlier time they shared one continuous chain of mountains, one connected set of river systems, and one broad continental interior. How do scientists know that these distant lands were once joined? The answer lies in matching scars and traces preserved in ancient rocks. Scientists have mapped long belts of deformed rock that run through Brazil and continue with the same structure in West Africa. Glacial deposits from late Precambrian ice ages show the same patterns of scratched bedrock and boulder-rich sediments in South Africa, India, Antarctica, and Australia, lining up as if carved by a single ice sheet. There is also evidence showing that identical groups of early animal fossils occur on margins that are now separated by entire oceans. These clues are powerful. When the shapes of the continents are moved back together using paleomagnetic data, the glacial grooves point in consistent directions, and the fossil belts reconnect into continuous zones. The result is a clear image: a supercontinent straddling high southern latitudes, with broad plateaus and long mountain arcs wrapped around the South Pole. Gondwana was real, and it played an important role in controlling the global environment. At times, large ice sheets covered significant parts of Gondwana's surface. Thick ice caps advanced and retreated across what is now the Sahara Desert, central India, eastern Brazil, and the edges of Antarctica and Australia. These shifting masses of ice changed sea level, redirected ocean currents, and altered wind patterns. Could such changes in circulation have helped drive oxygen into the oceans, feeding the rise of complex life? Many scientists think so, because major evolutionary radiations follow soon after these glacial episodes. As Gondwana stabilized, it became the southern anchor for later continental configurations. When Pangea finally assembled hundreds of millions of years later, Gondwana formed its entire southern half, locked against northern blocks like Laurasia. The Jurassic and Cretaceous landscapes that supported giant sauropods and powerful meat-eating dinosaurs stood on crust that had already endured earlier supercontinent cycles. Under the floodplains, deserts, and coastal swamps of the dinosaur world lay the old foundations of Gondwana, carrying ancient scars beneath younger sediments. In the next stage of this story, those foundations would begin to crack again. As rifts opened and new oceans formed, Gondwana itself would be torn apart, shaping the continents and environments that later predators would inherit. What happened when this southern giant finally broke? As Gondwana's foundations began to shift, another revolution was already written into the planet's crust. Many millions of years before dinosaurs left their powerful bite marks in bone, the rearranged continents of the early Paleozoic helped ignite one of the most dramatic biological events in Earth's history: the Cambrian explosion. Around 541 to 520 million years ago, the fossil record changes almost overnight in geological terms. In rocks only a few meters apart, scientists see a world go from simple, soft-bodied life to one packed with animals that have shells, armor, legs, eyes, and teeth-like mouthparts. Most major animal body plans appear in this relatively brief interval. It is one of the most important turning points ever recorded in fossils. This burst of innovation did not happen in isolation. Before the Cambrian, the supercontinent Rodinia had broken apart, and its fragments were slowly gathering into a new southern giant, Gondwana. As these blocks collided and stretched, they created long rift valleys, flooded lowlands, and wide continental shelves. Shallow seas spread across the edges of the forming continent. These sunlit waters formed broad platforms where nutrients, light, and oxygen came together in powerful combinations. When continents split and crash together, mountain belts rise and then slowly wear down. The strong peaks built during the assembly of Gondwana began to erode, sending sand, mud, and dissolved minerals into nearby seas. Scientists have found evidence showing that this erosion delivered pulses of phosphorus and other key nutrients to coastal waters. In these zones, algae and microbes could bloom, pumping more oxygen into the oceans and atmosphere. New environments appeared, and with them, new ecological opportunities. At the same time, the changing arrangement of land and sea altered ocean circulation. Narrow seaways and broad inland shelves guided currents in fresh patterns, mixing surface waters with deeper layers. Geochemical signatures in ancient rocks show rising oxygen levels in many basins just before and during the Cambrian explosion. In these better ventilated seas, animals could support more active bodies, stronger muscles, and more complex nervous systems. Predators could chase, prey could flee. This set the stage for Earth's first great arms race. Trilobites and other early arthropods developed hard exoskeletons and spines. Burrowing animals dug into the seafloor to escape attack, churning sediments that changed the chemistry of the seabed. In turn, new predators evolved, grasping appendages, slicing mouthparts, and armor-crushing structures that functioned almost like primitive teeth. Could such escalating defenses and weapons have emerged in a low-oxygen, simple environment? Behind these dramatic scenes lay the quiet work of vanished continents. The cycles that built Rodinia, tore it apart, and assembled Gondwana played an important role in setting oxygen levels, nutrient flows, and ocean routes. Without that tectonic groundwork, the armored bodies, complex food webs, and hunting behaviors of the Cambrian seas might never have appeared in the way fossils reveal. This early arms race would echo through time. The same planetary engine that fueled Cambrian predators would, many millions of years later, build the landscapes and climates that hosted the most dangerous dinosaurs. What other hidden links between drifting continents and deadly hunters remain buried in the rock record? For many millions of years, Gondwana was not a land of deserts and warm rivers, but a frozen engine of climate change. During the late Carboniferous and early Permian, a supercontinent parked over the South Pole turned into one of the most powerful ice-making machines in Earth's history. Across what is now South America, Africa, India, Australia, and Antarctica, thick ice sheets crawled outward from high, cold plateaus. As they moved, they scraped and carved the land beneath. In ancient bedrock, scientists have found long, parallel grooves called glacial striations, cut by rocks frozen into the base of the ice like rough teeth. Mixed layers of mud, sand, and scattered boulders, glacial tillites, sit above them, direct evidence showing that heavy ice once ground across these regions. Why did Gondwana freeze so deeply while other parts of the planet stayed more temperate? Its position over the South Pole placed vast areas under low-angle sunlight for much of the year, allowing snow to build rather than melt. At the same time, mountain ranges rose as Gondwana's strong crust collided and thickened. High elevations stay colder, so these mountains became centers where ice could accumulate, merge, and spread. Together, polar latitude and towering relief created ideal conditions for repeated glacial advances and retreats. The atmosphere itself helped lock in the cold. During the late Carboniferous, dense swamp forests flourished along tropical belts, far from the ice but still tied to Gondwana's shifting plates. These forests buried huge amounts of carbon in peat that would later harden into coal. Scientists have chemical evidence showing that this long-term drawdown of atmospheric CO2 reduced the greenhouse effect and allowed global temperatures to fall. Continental layout, mountain building, and plant evolution all played an important role in pushing the planet into an ice age state. Each time the Gondwanan ice sheets grew, so much water became trapped on land that global sea levels dropped. Shallow continental shelves were exposed, turning seafloors into cold, windswept plains. When the ice retreated, meltwater rushed back to the oceans, flooding those same shelves again. Coastlines shifted hundreds of kilometers, drowning some ecosystems while opening new habitats elsewhere. Climate belts moved with the changing seas, squeezing tropical zones and expanding cool, dry regions. Entire communities of marine life had to adapt, migrate, or vanish. These swings were more than regional weather changes. They were a warning of how dangerous a supercontinent's configuration can become. The stresses of repeated glaciations weakened ecosystems and altered ocean circulation, priming the Earth system for the harsher crises of the later Permian. As Gondwana's ice finally waned and climates warmed again, new environmental pressures would rise, leading toward mass extinction and clearing ecological space that, much later, would be filled by dinosaurs. What happens when the same drifting plates that once built icebound Gondwana assemble an even larger supercontinent under a different sky? Those same drifting plates did not stop with the end of Gondwana's ice. Over many millions of years, they carried this southern giant steadily toward the equator, and then toward the crowded margins of the northern continents. Calm oceans and scattered islands would give way to one of the most dramatic collisions in Earth's history. By the late Paleozoic, Gondwana was on a slow but relentless journey northward. Ahead of it lay Laurussia, a large landmass already formed from the earlier merger of Laurentia, Baltica, and Avalonia. Between them, an ocean narrowed grain by grain as seafloor was pulled down into subduction zones. Scientists have found evidence showing that between about 335 and 300 million years ago, that ocean finally vanished as Gondwana rammed into Laurussia, welding the fragments into the supercontinent Pangea. These collisions did not just close oceans, they crushed crust into mountains. Along the collision belt, rocks buckled, folded, and stacked into ranges that once ranked among the most extensive on the planet. The ancestors of the Appalachian Mountains rose where eastern North America met Gondwana, while farther inland, the central Pangean Mountains formed a high, rugged spine. In some regions, rocks were pushed so deep that their minerals record powerful heat and pressure, silent traces of vanished peaks that may have rivaled the Himalayas. A single landmass stretching nearly from pole to pole transformed the global environment. With so much land joined together, moist ocean air could not easily reach the interior. Vast regions far from any coastline dried out, turning into broad desert belts marked by shifting dunes and seasonal rivers. At the same time, the contrast between hot interiors and cooler coastal zones strengthened monsoon systems along the edges of Pangea. Seasonal winds would have brought intense rains to some regions and long droughts to others, creating sharp climate boundaries across the supercontinent. These tectonic and climate shifts played an important role in reshaping life. When Gondwana met Laurussia, animals and plants that had evolved in isolation suddenly shared the same connected land. Fossils from this time show seed ferns, early conifers, and giant club moss forests spreading across wide areas, while amphibians and the first reptile-like vertebrates moved along new river systems. What happened when predators and prey from different continents met for the first time? New competition, new opportunities, and new vulnerabilities followed. As Pangea matured, its extreme climates and linked ecosystems also set the stage for crisis. Large regions of arid land, fluctuating sea levels along its coasts, and long-term volcanic and tectonic activity stressed many species. Scientists have gathered evidence showing that these combined pressures built toward the end Permian mass extinction, one of the most devastating biological losses in Earth's history. The completed Pangea was both a triumph of plate tectonics and a loaded gun, primed to fire a catastrophe that would clear the way for the age of dinosaurs. The completed Pangea was both a triumph of plate tectonics and a loaded gun, but it was also part of a much older pattern. For millions of years before its final assembly, Earth's surface had been gathering and scattering continents in a slow, powerful rhythm. Pangea was not a one-time accident. It was simply the latest in a long lineage of supercontinents. Scientists have identified earlier giants with names that sound almost mythic: Valbara, Ur, Kenorland, Columbia, Rodinia, and Gondwana. Each formed from smaller blocks that collided, thickened, and welded together, then later tore apart again. The crust that built Pangea had already lived many lives. Ancient cratons inside Africa, North America, and Australia preserve zircons and other minerals that formed many millions of years before Pangea existed, carrying chemical signatures from vanished oceans and lost mountain belts. This deep history means that by the time Pangea came together in the late Paleozoic, Earth's continents were no longer young and thin. They were strong, buoyant rafts of rock that had been recycled and reworked through multiple cycles of collision and rifting. Subduction zones had dragged older crust into the mantle, while surviving cores rode upward to form the backbone of new landmasses. Pangea was the temporary summit of this long tectonic staircase. As a physical structure, Pangea was one of the most dramatic land configurations in Earth's history. Almost all major land areas were fused into a single, mostly continuous mass that stretched from pole to pole. The interior lay far from the sea, creating extreme continental climates with vast hot deserts, seasonal droughts, and strong temperature swings. Around its edges, long coastal margins faced a global ocean called Panthalassa, where powerful currents and storms shaped marine environments and influenced climate on land. There is evidence showing that earlier supercontinents also produced climate extremes, from intense ice ages to hothouse intervals, and these shifts repeatedly triggered evolutionary turnovers. Entire groups of organisms declined, while new groups expanded into the gaps left behind. This pattern played an important role in shaping the biosphere that existed when Pangea finally formed. By the late Permian and early Triassic, the supercontinent's harsh interiors and broad coastal plains were already selecting for hardy, adaptable animals. Why does this matter for dinosaurs? Because the same tectonic forces that built Pangea would eventually tear it apart. As rifts opened and new oceans formed, the single supercontinent fragmented into isolated pieces, each with its own climate, coastlines, and ecosystems. This emerging Mesozoic world became a patchwork of separate arenas, where different dinosaur lineages evolved in relative isolation. In some regions, giant plant eaters spread across humid lowlands. In others, dry basins and coastal deltas created very different challenges. On each continent, predators responded. As Pangea broke, it set the stage for regional dynasties of carnivorous dinosaurs, allowing some of the most dangerous hunters in Earth's history to dominate their own domains. The ghosts of older continents still shaped every step they took. The ghosts of older continents still shaped every step they took. But those ghosts are part of a much larger pattern. For millions of years, Earth has been building and breaking giant landmasses in a slow, powerful rhythm that controls oceans, climate, and, in the end, which animals rule the surface. Long before Pangea, there was Gondwana, a southern giant tying together what is now Africa, South America, Antarctica, India, and Australia. Before that stood Rodinia, a supercontinent that gathered most of Earth's land around a single equatorial bulk. Earlier still came Columbia, also called Nuna, followed by even more shadowy ancestors, Kenorland, Ur, and at the edge of the rock record, Valbara. Each one rose, locked its fragments together for tens or hundreds of millions of years, and then slowly tore apart. This repeated story is known as the supercontinent cycle, and it is one of the most important large-scale processes on the planet. Driven by plate tectonics and deep mantle convection, hot material rises from Earth's interior, while colder, heavier plates sink back down. Over many millions of years, this circulation drags continents across the globe, first pulling them together into a single mass, then stretching and rifting them into scattered pieces again. Scientists have found evidence showing that this is not random wandering. When continents collide, their edges crumple into long mountain belts, welding separate cratons into a single body. When they split, great rift valleys form, later becoming new ocean basins. Matching belts of deformed rocks in South America and Africa, or in India and Antarctica, reveal ancient collisions that no longer line up on a modern map. To reach further back, scientists turn to even smaller traces. Tiny zircon crystals, some more than 4 billion years old, carry chemical signatures that point to early vanished continents whose original surfaces are gone. Paleomagnetic signals frozen into ancient lava flows show which way Earth's magnetic field pointed when the rocks cooled, revealing how far north or south each craton once sat. Together with the strong, stable cores of old cratons themselves, these clues act like scattered fossils of geography, allowing researchers to rebuild worlds that no longer exist. These shifting continents played an important role in shaping climate. When Rodinia broke apart, fresh rock weathering and changing ocean circulation helped trigger extreme ice ages, including possible snowball Earth episodes when ice reached near the equator. When Gondwana and later Pangea assembled, vast interior deserts formed, while long coastlines and new seaways redirected warm and cold currents. Life responded every time the continents moved. Oxygenation pulses in the oceans, evolutionary radiations after harsh glaciations, and new shallow seas along rifted margins created changing environments that favored different organisms. By the time Pangea finally split, this ancient cycle had already prepared the stage with diverse habitats, guiding the rise of dinosaurs into many separate realms. If such a pattern has ruled the deep past, what might the next supercontinent mean for the future world? By the time Pangea split apart, the world that dangerous dinosaurs inherited had already been forged in far older collisions. Long before the first tyrannosaur bit through bone, entire supercontinents had formed, shattered, and vanished, each one reshaping oceans and air. The predators of the Jurassic and Cretaceous were powerful, but the most relentless architect of their environment was the planet itself. Many millions of years before Pangea, an earlier giant called Rodinia gathered most of Earth's land into one broad mass. Its breakup scattered crustal fragments that later drifted and locked together again, helping to assemble Gondwana in the south. Scientists have evidence showing that the same ancient cores of Africa, South America, Antarctica, India, and Australia once sat side by side, stitched together by long mountain belts. Those mountain chains were the crushed scars of Rodinia's wreckage, recycled to build the foundations of later worlds. As Gondwana grew and slid across the globe, it did not move alone. Other continents, carrying their own fragments of older crust, slowly closed in. Over tens of millions of years, collisions raised strong mountain ranges from Appalachia to Central Asia. These impacts played an important role in forming Pangea, a landmass so vast it altered wind patterns, rainfall, and the routes of entire ocean currents. Without this deep history of assembly, the familiar Jurassic map of separated continents would never have existed. Each breakup and collision changed how the oceans breathed. When supercontinents rifted, new seafloor formed and mid-ocean ridges pumped heat and chemicals into the water. Narrow seaways opened, guiding currents into new paths that carried oxygen and nutrients to different depths. On the edges of Gondwana and later Pangea, shallow continental shelves became broad factories of life, where algae and other organisms filled the water with organic matter. Over time, this biological engine helped raise oxygen levels in the atmosphere and ocean, making large, active animals possible. The result was a stepwise increase in ecological complexity. After earlier supercontinents broke apart, coastlines multiplied and climates diversified, creating isolated basins, flooded plains, and seasonal interiors. Scientists have found fossils from these intervals that record the rise of complex animals in the seas, followed by the spread of vertebrates onto land. Each rearrangement of land and water forced life to adapt, experiment, and radiate into new forms. Some of the most dramatic evolutionary leaps were tied to these shifting continental designs and their climate shocks. By the Jurassic, this long sequence of experiments had produced the lush conifer forests and fern-covered valleys where predators like Allosaurus hunted. By the Cretaceous, high sea levels and active rifting created vast inland seaways, such as the one that split North America and supported giant fish and marine reptiles that shared the environment with Spinosaurus and other hunters. The dangerous dinosaurs of this film were not accidents. They were the sharp edge of a planet that had spent billions of years testing different worlds. If Earth's restless plates could build such predators from ancient rock and shifting oceans, what new forms might future supercontinents create? Long before the age of giant dinosaurs, Earth was already building and erasing entire worlds. Those vanished continents left no coastlines, no islands, no visible traces in the modern environment. Yet beneath the surface, there is powerful evidence showing that these lost worlds were real. One of the most important clues comes from ancient cratons. These are the thick, strong cores of continents, made of very old stable rock that has survived for billions of years. Cratons in South Africa, Western Australia, Canada, and Greenland contain rocks more than 3 billion years old. Scientists have used their chemistry and structure to show that they once sat together as parts of early supercontinents such as Valbara and Ur. The cratons act like the deep roots of a forest that has been cut down. The trees are gone, but the roots still mark where they once stood. Even older clues are locked inside tiny zircon crystals. These hard, durable minerals can survive long after the rocks that carried them have been destroyed. Some zircons from the Jack Hills of Australia are about 4.4 billion years old, older than any known mountain range or ocean floor. Their internal chemistry records that they formed in conditions similar to continental crust, with liquid water at the surface. Scientists have taken this as evidence, showing that early fragile continents existed many millions of years before any surviving rock. Then were recycled back into the deep interior of the planet. Paleomagnetism adds another layer to this detective story. When volcanic or sedimentary rocks formed, tiny magnetic minerals inside them aligned with Earth's magnetic field, like frozen compass needles. By measuring the direction and strength of that ancient magnetism, scientists can tell where on the globe those rocks once sat and how far from the equator they formed. Rocks from distant cratons in South Africa and Australia, for example, record-matching magnetic orientations at the same age, indicating that they were once joined in a single landmass. The continents have moved, but their magnetic memories remain. All of this is cross-checked with other lines of evidence. Long mountain belts of the same age and rock type reappear on opposite sides of oceans, like torn pages from one book. Fossils of the same early life forms, and later of plants and small animals, match across continents that are now far apart. Geologists also compare the chemistry of ancient lavas, the direction of folded layers, and the deep roots of mountain chains. Again and again, separate clues point to the same ancient maps. Is this just a set of clever guesses, or a real reconstruction of Earth's first supercontinents? The agreement between cratons, zircons, paleomagnetism, and matching mountain belts has played an important role in building confidence. Together, they reveal not a single lost continent, but a whole sequence of worlds that rose, joined, and vanished long before the first dinosaur bone hardened in the mud. The next step is to ask how those shifting worlds shaped the rise of life itself. Those shifting worlds also point towards something even stranger. If continents like Valbara and Keinorland can be reconstructed from scattered hints, what about the worlds that left almost nothing behind? Some scientists have begun to speak of ghost continents, ancient landmasses so old and so broken that only the faintest signals remain. For many researchers, the story may not start with Valbara at all. There are proposals for even earlier supercontinents, sometimes called names like OR1 or other hypothetical pre-Valbara landmasses. These ideas come from tiny pieces of evidence showing that some of the oldest cratons on Earth might once have been joined in different ways. Detrital zircons more than 4 billion years old, preserved inside younger rocks. Hint that strong, stable continental crust may have formed, merged, and vanished many millions of years before any recognized supercontinent appeared. This kind of reconstruction is one of the most difficult challenges in geology. The earliest rocks have been cooked, squeezed, and shattered by intense heat and pressure. Plate recycling drags whole regions down subduction zones into the mantle, while metamorphism overprints original textures and minerals. Erosion strips away mountains grain by grain, carrying their fossils and their history into the sea. Over billions of years, these forces have erased coastlines, mountain belts, and rift valleys that once played an important role in shaping the planet's surface. To see how easily a continent can disappear, it is enough to look at a modern example. Zealandia is a nearly continent-sized block of crust beneath the southwest Pacific, with only New Zealand and a few islands rising above the ocean. Scientists have mapped its strong, thick continental crust under thousands of meters of water, showing that a genuine continent can be stretched, thinned, and mostly drowned without being completely destroyed. Other submerged microcontinents, such as fragments buried beneath the Indian Ocean or hidden around Madagascar, tell a similar story of broken worlds scattered across the seafloor. If such large fragments are still being discovered under today's oceans, what has been lost from the far deeper past? Some models suggest that before Valbara there were earlier cycles of assembly and breakup, perhaps several generations of supercontinents that rose, collided, and sank back into the mantle. Their rocks would have carried fossils of early microbial life, magnetic directions, and chemical signatures of their environment. But almost all of that record has been recycled. This means that current reconstructions may show only the visible part of a much larger, hidden history. Beneath the oldest cratons, seismic waves hint at strange, dense roots that could be relics of long-vanished continents. Deep in the mantle, geochemical anomalies may preserve traces of crust that sank billions of years ago. How many entire worlds have come and gone, leaving only microscopic crystals and subtle signals in Earth's interior? In many ways, the missing chapters of the planet's story are more mysterious than any dinosaur thriller. And the next step is to explore how those lost worlds might still echo in the rocks that remain. Those faint echoes in ancient rocks are not just memories of lost worlds. They are warnings that the story is still moving. The continents that carried dinosaurs and later humans are not fixed frames in a film. They are actors in a long, slow collision that has not yet reached its next climax. For millions of years, Earth's surface has been shaped by plate tectonics, the powerful engine that drags continents together and tears them apart. Scientists have used computer models, magnetic data, and seismic images of the deep interior to project this motion forward. The results are striking. Several possible future supercontinents have been proposed, with names like Pangea Ultima, Amasia, and Novopangea. Each is a different answer to the same question: where will the wandering fragments of today's world finally meet again? In one scenario, the Atlantic Ocean closes and the Americas slam back into Africa and Europe, rebuilding a Pangea-like mass near the equator. In another, the Pacific disappears instead, and the continents cluster around the North Pole to form Amasia. There is also evidence showing that new subduction zones could grow around the Atlantic, guiding the plates into a very different pattern called Novopangea. No single outcome is certain, but all share the same core idea. The present arrangement is temporary. What would life be like on a future supercontinent? A giant landmass creates vast continental interiors, far from any ocean. Those interiors tend to be dry, with extreme heat in summer and intense cold in winter. ocean circulation would be reorganized, changing how heat and nutrients move around the globe. New mountain belts would rise where continents collide, just as the Himalayas formed from the impact of India with Asia. These changes could drive drastic shifts in climate. Could there be new ice ages along the margins, while the center bakes under long droughts? Humans evolved on a planet with scattered continents and many coastlines, an arrangement that allowed diverse climates and rich coastal environments. That pattern played an important role in shaping migration routes, food sources, and the spread of civilizations. Yet on geologic timescales, this is only one of the most short-lived experiments in continental design. Many millions of years from now, the map that seems familiar and permanent will be unrecognizable. Seen from this perspective, every city, every fossil bed, and every mountain range is a snapshot taken during an active experiment. The ground beneath modern feet rides on plates that slide a few centimeters each year, but over tens of millions of years, those small motions will close oceans and weld continents into a new whole. The same deep forces that once assembled Valbara, Rodinia, and Pangea are still working, silent and relentless. In the next chapter, the focus turns to how this ongoing tectonic engine may shape the long-term future of climate and life, long after the present coastlines have vanished. Those deep forces have been active since the first crust cooled on a glowing, magma-covered planet. For millions of years, Earth was an ocean of fire and impact craters, its surface reset again and again by collisions and molten rock. Yet out of that violent beginning, the first fragile continents emerged, thin rafts of lighter rock trying to float on a restless mantle. From there, the story followed a chain of vanished worlds. Early landmasses such as Valbara and Ur formed many millions of years ago, long before dinosaurs or forests, when the atmosphere and oceans were still changing. Later, larger supercontinents like Kenorland and Columbia, also called Nuna, gathered scattered cratons into broad, rocky shields. Each one assembled, stretched, and finally broke apart as heat and pressure forced the plates to move. Rodinia rose as one of the most dramatic of these configurations, its combined land helping to trigger extreme ice ages that may have frozen the oceans almost to the equator. After Rodinia split, Gondwana and then the great supercontinent Pangea took shape, setting the stage for familiar chapters in Earth's history. The positions of these continents played an important role in shaping climate, ocean currents, and the environments that later supported giant reptiles and eventually dinosaurs with powerful jaws and strong bones. Scientists have built this timeline from scattered clues, ancient zircons, deeply eroded cratons, and faint magnetic signatures in very old rocks, provide evidence showing that entire continents once existed to where only ocean lies today. Seismic waves traveling through the deep interior even hint at sunken fragments of long-lost plates, carried downward at subduction zones and stored like geological ghosts far beneath modern cities and coastlines. This means every forest, every highway, every building stands on the ruins of older worlds. The stable rock underfoot is not just a foundation. It is an archive of collisions, rifts, and vanished mountain chains. The continents seen on maps are only the latest frame in a long, dangerous experiment in planetary surface design, constantly re-edited by plate tectonics and deep mantle flow. With this in mind, even ordinary landscapes begin to change. A folded mountain ridge becomes the crushed edge of an ancient collision. A smooth beach marks the temporary border of plates that will not stay still. A small rock in a garden wall might contain minerals that formed when Rodinia was whole, or when Valbara first gathered above a restless sea. Scientists have shown that careful observation can turn such everyday scenes into records of deep time. Fossils in a roadside cliff, ripple marks in sandstone, or the alignment of crystals in a hand-sized stone all carry evidence showing that this planet has rebuilt its surface again and again. Seen this way, Earth becomes the ultimate dangerous world builder, a planet that raises continents, populates them, and then tears them apart. What other hidden chapters remain buried beneath the oceans? or locked inside crystals older than any known mountain range. To follow those clues further, it is vital to support Earth science, value geological research, and keep exploring deep time through books, museums, and field discoveries. For those who wish to understand how the age of dinosaurs and the modern world were both shaped by the same tectonic engine, the journey does not end here. It continues in every rock, every landscape, and in the next story that uncovers the powerful forces beneath the surface.